The monitor thingy, sorry about this, but we will get it fixed. There seems to be random issues on some laptops. I had these issues yesterday, so we started my topic 10 minutes late. Let's see how, it's going to take a few minutes, and then we get that fixed.
I think that you broke it.
I did, and I broke this too. I walked close by. That's enough for technology. I'm a chaos monkey. How many of you were at the party yesterday? How was it?
Great.
There was 1 thumbs up. That counts as a favorable review. 5 out of 5 in Yelp. Thank you. We've been thinking of doing a party business. Do I need to talk long?
Yes.
Oh, thank you. He just threw me under the bus. The panel? How was that? How many of you attended panel yesterday? Quite many. Did the panelists, I got some questions yesterday from the speakers that they weren't sure if they were just chatting with each other or, if the audience was interested. Were there discussions of the panelists yesterday? Were they something that touched you? Were they interesting? I don't know who should respond. You, sir.
I wasn't there, sorry.
Oh, excellent. You, sir. Sure. Let's go with that. Thank you for the feedback. Let's not ask any more questions. Any feedback from yesterday? Anything we could do better? No? Write it to survey. We're going to have a second survey today at the end of the day, day 2 survey. And, that's double the opportunity of winning the drone. So, yeah, the day 1. Do you want to see the day 1 QR code again? Excellent. Excellent. Let's do it today. End of day, I guess.
I can try to show it to you, but you have to do it very fast.
Do you have your mobile phone open? If it flickers there, like I think, lower the hertz so it flickers slower. All right. Sorry about this. Take a break, talk with a friend. We are going to begin immediately when possible. Thank you.
Nyt viimeinen vaihtoehto vielä tästä. Muutetaan.
Nyt on ollut yllättävän pitkään.
Anteeksi?
Nyt on ollut yllättävän pitkään kuva.
Se on nyt extended wide.
Ei kun kato, se on se SD-purki, niin kun mä oon vähän kohti teidän SD, nyt teillä ei mene niin siihen. Se SD-purki, joka menee streamiin, se vaikka. Koska tähän meidän järjestelmään kuva menee, niin periaatteessa koko ajan. Mä nyt otin sieltä toiseksi. Ota.
Nyt kuva pysyy.
Joo, eli se menee suoraan meille. Nyt mulla on niitä täällä. sieltä se tulee.
Pystyykö sä
Onko sulla niinku huomioista? Meneekö sulle tästä itse asiassa kuva? Tästä katso.
Meneekö sulle?
Sitten sen sulle SDI täältä.
Okei, no nyt tuleeko?
Onko sulla kuva?
Näyttäis tulevan. Okei, hei!
Tällä turhasti täällä yksi kaakka.
Don't touch anything. Do your speech like that. No moving.
Se kappis.
Yeah. What did you move? Odota vähän. Lähteekö nyt toimii? Se ei ollut tää Scandikin arakteri kanssa, mikä
Ei, siis meillä kaikki ihan normaali. Tässä on toi streami menevä, niin tulee jotain paikoita, niin jollain tavalla. Ei ole ihan.
Kokeillaan ei ottaa tää arakteri vielä pois, otetaan extendedinä ja nää astus.
Tuliko nyt?
Okei, tää toimii. Oksia kuvat. Okei, arakteri pois. Virta sisään. Edelleen. All right, let's start the day two. Sorry about this. Thank you for your patience. Let's welcome to the stage Jonas Westlin.
Testing, testing. Hello, hello.
Yeah, you can push it a little bit closer to your mouth.
Yeah. Hello, is this better? Hello, hello.
You find that? Cool.
Yes.
Yes. Yeah. Hello, everyone. Welcome, and sorry about the delay. We had some issues getting a display out to the screen, and as well as the stream. So, yeah, gonna start a little bit late here. We're gonna try not to talk faster because I think I have a lot of stuff to cover. And just a reminder here about the Wi-Fi, and there is electricity available as well. Some places, maybe not for everyone, but try to share them. And there was the introductions about FAUG and all this stuff. And I think you know. Lunch is going to be over there, and toilets are over there. Cool. And thank you for choosing my session for the morning. And there's those ones. You can see the schedule on iglooconf.fi. And the live stream is available at azure.ly/igloo1 or igloo2. This is igloo1 here in Arrakis. Yeah, so without further ado, so my presentation is on real-time asset tracking. It's basically based on a customer case that we had to implement. So I'd like to kind of discuss those kind of things with you as well. And I did do this presentation a while ago at Tekorama. I don't know was anyone here at Tekorama in Belgium? Yeah, I know Rick was. Oh, excellent. That's good. So this is all new for most of you. Well, actually, Rick, you didn't see my presentation either, right?
I'm looking forward to this one.
Exactly. Awesome. So my name is Jonas. I work as a developer/software architect at Azure. And I've been working with this Azure stuff for around 9 years at this point. I'm an Azure MVP as well. Wanted to include this slide because I thought it's funny. If you want to try to find me in this photo, it's a bit of a Where's Waldo kind of situation because Olli's magnificent face is right in front of me. But yeah, that's our company. We have offices here in Helsinki, Denmark, and Belgium. So for the agenda, first we're going to look at the business case of the thing we had to implement, and as well as the architecture. Then right away we're going to get into the demo, which you can test out as well. And then we're going to talk about the fun topic of coordinate systems. I know, at 9 a.m. in the morning, my favorite thing. And then we're going to talk about a little bit of performance optimizations that we could do here. And we'll maybe have some time for Q&A. If we don't have time, then you can just catch me later after the presentation. Also, if you have any questions during the presentation, just raise your hand. So, the business case. So, we have a customer who has a bunch of what they call assets, but that are essentially trucks, containers, this kind of stuff. And they want to know where those are. They also have a bunch of factories, kind of, those trucks also go into other kind of logistics hubs, ports, this kind of stuff. And so they want to know where those trucks or their assets are at each time. And also they want to know when these assets enter one of these logistics hubs or factories, and as well as when they exit them, of course. And I'm just going to forward this one. And the main thing that we also get from that is that we get statistics on kind of how long it takes to unload at this location, how long it takes in transit between A and B, and so on. Data which can be then used to optimize logistics. So some requirements from the customer. They would like to have a quote-unquote real-time locations of these assets on a map. And the developers in the room know that real time is a relative thing. It depends kind of what the actual requirement is. It's just that when we hear real time, we are like, okay, it needs to have a direct TCP link to the customer's like PC, basically. It's not usually the case. Usually if it arrives within like 1 minute, it's considered a real time. In this particular case, actually, like 5 to 10 minutes was totally fine, actually, as a delay, so it's quote-unquote real time. The trucks, they don't move very fast. So, yeah, they're not really going to lose them in 5 minutes. The geofences for each location can be any polygon. So remember, we had this like factory area. Well, how do you define what is the area, right? We could just make it a circle, basically make it like, okay, if it's within this distance of it, then it's considered inside it. But we went a bit more fancy. We want to allow whatever polygon, so you can just draw like whatever shape you want around the area. And if it's inside that, it's considered in that. And we're going to store the date and time whenever a vehicle enters or exits a geofence. Get some notifications on the map view as well when these events occur. Want to keep these location events as well for a couple months for analysis. Don't need to keep them longer than that. There's also quite a lot of that data. And want to also allow authorized users to change the device configuration straight from the map view. Okay, so for the architecture, just going to go through this kind of piece by piece, so it's a bit easier to digest. So the first part of our architecture here is, of course, we need to get that data somehow to the cloud, right? So we're going to use Azure IoT Hub for that. And it's like, okay, well, we could use something like Azure Event Hubs as well, right? That's also a good service for doing data ingestion, right? But we actually also want to be able to change configurations and stuff. So IoT Hub gives us that bi-directional communication. And then we're using device provisioning service to automatically provision those devices, so we don't have to manually configure each device in IoT hubs. And so DPS, or device provisioning service, the whole point of it is just to make it much easier to register IoT devices at scale. So essentially you configure how they authenticate in DPS, and then when it boots up for the first time, it connects DPS. Hey, I'm this device, this is my authentication, and DPS is like, okay, looks good. I've registered you in this IoT hub. Go ahead and connect there. The one nice thing about it is that you can configure this allocation policy, which basically decides which IoT hub is chosen for the device. And you can make it so that it uses the closest location, for example. So if you have multiple IoT hubs, you can configure it so that it will select the IoT hub that's closest to the device. And the IoT hub is our telemetry sync, and gives us that bidirectional communication. So once we have that data in the cloud, we're going to actually forward it to an event hub. Now, strictly speaking, this event hub is not necessary in this architecture. IoT hub includes an event hub compatible endpoint that we could also use. There was a couple reasons. In the actual business case, we actually had events coming from other sources than IoT hub as well. So the event hub was essentially the common place where all of the events came. But yeah, so in this particular sample case, it's not exactly necessary, but we still have it there. And we get the data from there over to Data Explorer, where we're keeping it for a couple months. And then we're getting the location updates to a function app, from which we actually check whether they've entered the geofences or exited them through an Azure SQL database. So yeah, the event hub that we have there is a very, very large-scale data ingestion service. Mainly, the scaling in it is done through these partitions because, you know, I/O and maximum kind of IOPS is a thing. So it splits it to partitions so that you can ingest more data and also process more data simultaneously. One key thing to understand about event hubs is that it is an event log, it's not a queue. So when you process a message from an event hub, it's not deleted. It's basically just a buffer, and the events are deleted when their time to live expires, essentially, from the end. So they're not gone until that. The processing is in order as long as it's within the partition, so you have to choose your partition key pretty carefully. In IoT scenarios, it's typically the device ID. It's kind of a natural choice. Now, ADX, or Azure Data Explorer, it's a bit overkill for this use case. I say this because ADX is what is actually powering Azure Monitor. So, you know, when you run Custo queries against it, you're running them against ADX. They made a blog post about it some time ago where they explained that they're processing something stupid like a petabyte a day. There it's just, yeah. In the business case, we originally used the time series insights. RIP. So after we had deployed like 20 of those, Microsoft informed us that they are actually going to kill this service. Thank you. And told us to go to ADX, which was like 5 times more expensive. So, yeah, nice. It is really massive scale, though, and we can do native ingestion from Event Hub. That's like really easy. It was easy in Time Series Insights, too. It also supports geospatial analysis, which is nice. And we could also use Cosmos DB here. The only problem with Cosmos DB is that you will have to very carefully design your model, and you'd most likely have to make it write optimized here because there's a lot more writing happening than reading. And yeah, it's a little bit more complicated. Then we have Functions, which is the serverless application platform. How many of you here have used Functions? Oh, yeah. Good. Then we have an SQL database. So SQL Server supports spatial data. We can do spatial kind of stuff there as well. The business case already had an SQL database, so we were like, well, we can just use that, right? So that was one reason. But it is also not a bad choice here, actually. You can use Cosmos as well, but I'll get back to Cosmos a bit later. So then we have our front end, essentially here in the sample app. So we have a function app that is containing the front end files. It handles the real-time SignalR connections and all the API calls from the front end as well. So we're using SignalR for real-time communication between the front end and the back end. And then we are using Azure Maps for the map content itself. So we have those map tiles being loaded from there. So in this use case, we only use maps for that. It does have other features too, like if you want to do lookups, basically you can give it a set of coordinates and it'll give you back an address, or you can do it the other way around. You can do kind of point of interest searches and stuff like that. The other really good part about maps was that the billing is within the same Azure subscription instead of having to make like a Google account and having another billing. And in this business case, the customer was a bit of a bigger enterprise and didn't have a Google account also. So basically when they said that, I was like, okay, so we're not going to do that, because I knew it's going to be like months and months of meetings and stuff to get that account. And it's like, no, it's not worth it. Then we have SignalR service. How many of you here have used SignalR? Quite a lot, yeah. So it's basically for real-time communication over WebSockets. SignalR, when it was kind of invented, the big thing about it was that because a lot of browsers didn't support WebSockets, so it allowed kind of fallback to other methods that would work. But from the developer's point of view, you wouldn't have to do anything different. So it was really good. Nowadays, WebSockets are pretty ubiquitous, though. But the big thing about SignalR service is that it allows us to scale the WebSockets separately from our backend. So because you can only have a limited amount of these connections in your backend servers, so this allows us to scale it completely separately, and the backends only have a few connections to SignalR service. Now, in this case, we are using functions, which, as you know, is serverless. So how are we going to do persistent connections? The answer is we are not going to do that. We are going to put this into serverless mode and allow functions to scale to 0 if it wants. So basically, that's how the whole sample architecture looks like. And one change that has happened there is that we now have a container app there instead of an actual vehicle. So just to say right now, a disclaimer, when I show you the demo, they're not actually, actual vehicles. They are simulated. Yeah. So without further ado, let's go to the demo. It's westl.in/igloo demo, or you can scan the QR code. Both of those work. We're going to try not to bring down the Wi-Fi, by the way, when I do this. But it's not that much data. Okay. Yeah, so I'm going to put that on the other screen. Yep. So that's how it looks like, the front end, essentially. So those are the simulated devices. They're going around Helsinki. Essentially, there's 2 routes that I've programmed in there, which they can choose to go in reverse as well. Yeah, so each of those is being simulated there. Let me, but currently we're running container apps on 3 instances, and each of those is running 10 simulated devices. So we're running 30 vehicles at the moment. But I think it would be more interesting to see how that scales. And this is one of the reasons why I picked container apps, by the way, because you can just very easily go here and do something like this. So we can say, let's go to 30 instances. So while that is deploying, we can also see kind of what happens over here. By the way, if your mobile device starts lagging when I do this, I'm sorry. Browsers don't necessarily like being bombarded with like 1,000 messages per second from the WebSocket. I've had that happen a few times. Just going to wait for the container app to scale out. Yep, there we go. I think I think it started to scale out. Okay, so one problem with this is that now it's maybe a little bit harder to show you what is going on there, but so also we are checking these geofences. So Helsinki Station has a geofence here. So whenever one of those is entering it or exiting, we're getting an event here as well. Those are being logged in SQL database as well in real time there. And also something that we can do as a logged in user, I can also go here and just change the parameters, which is pretty fun. Now, because we have a lot of devices there, you're probably not going to see this. So these vehicles turn out to have rocket engines, actually. It's not the prettiest UI I've ever made, by the way. As you can tell, I'm a software engineer, not a UX designer.
Isn't it? I think it might be the prettiest UI you ever made.
It might be, yes. Sake is correct. It might be the prettiest UI I've ever made, actually.
It's pretty nice.
Yeah. And then so the sample app, and by the way, this is all on my GitHub, so you can get the app there, get the whole app from there if you'd like. It also includes this Azure dashboard, which will give you a bunch of performance data from the data processors and such. So I think we are. Let's see how many we are processing right now. I think it hasn't updated yet. We were doing about 1,000 a minute there, but we should be doing tens of thousands a minute. Well, anyway, I'm actually going to scale down this one over here while we are waiting, as I don't particularly. This is the fun part of container apps, the portal. Okay, that looks good. Okay, let's scale it back down. And then we have our device provisioning service over here. I'll just quickly show you how that's configured. So we have an IoT hub linked. You could have several, obviously. We only have one in this case. Then we have our enrollments. So we have our production one here. I have one for local development there as well. And as you can see, we have an attestation mechanism. So this is how the devices authenticate. Here I'm using symmetric keys because it's much, much easier for a demo. I didn't particularly want to start fiddling around with certificates for some reason. But certificates or TPM is the approach recommended for production. And that the main reason is because there's only one key. Well, okay, two keys, but they're similar keys essentially. But what these keys allow you to do on the device is essentially become whatever device you want. I mean, the device can choose its ID. So you can just become another device with that key. So not particularly great for production scenarios, right? It's not the best security. Certificates are kind of nice because you can put a root certificate or intermediate certificate here, and then the devices just have a leaf certificate, and it all kind of just works. Well, I typically say that with certificates, and typically they don't work just like that, but still. Yeah. And that one is, of course, set to only provision to that one IoT hub always, but you could configure it in other ways as well. We can also look at the devices from here. There's going to be quite a few of them. But I can just show you kind of how the device twin looks like from here. So what we're using for configuring those devices is we're using these device twins in IoT Hub. And you can actually see here there's these kind of, well, the font is pretty small, so maybe you don't. But there's these desired properties over here. One of them is the speed over here. So what we can do is we can just change the number over here and hit save. And the device is going to receive that. And then if I scroll down, you also can see a similar one called reported properties. So these are the properties that the device is reporting back to IoT Hub. So essentially it allows us to confirm that the settings have been actually applied. You can also put other stuff there, of course. And so I picked a device that is actually not running anymore, so it's not updating this, but if it was, it would have updated the new setting over there. Then we have Azure Data Explorer over here. Let me just make that a little bit bigger. So one of the neat things that we can do with Azure Data Explorer is that we can also do spatial analysis. So we can, for example, plot those on a map view over here. And then we also have our SQL database, and this is kind of funny actually. So there's a similar feature in SQL Server Management Studio where you can get these like spatial results. So you can see the geofences over here, and you can see the kind of definition over here, the coordinate points essentially for the polygon. But you can also go to spatial results. Now, in SSMS, you actually get like a view, like a picture at this point, but the portal gives you an SVG. Now, what will the SVG contain? Cool. Thanks, Azure Portal. Excellent.
Looks like your UI.
Yeah, pretty much, yes. It looks like my UI. It's not much different. Actually, even the shade of blue might be the same. Yeah, but SignalR. Now, this is kind of interesting because so what we've done here with the SignalR service is that we've changed it from default service mode to serverless, and then we've configured this thing called an upstream. Now, because the SignalR service doesn't have a persistent connection to functions, what it instead has is if there's a message from a client to SignalR service, it will forward that message to our functions through this webhook. So the SignalR service kind of plugin in functions, it kind of provides this webhook for you. So you don't need to actually make this webhook. You just make the functions there kind of with the triggers and stuff that is in the documentation. It's pretty easy to use. Now, one really, really small thing that kind of threw me for a loop here is that there's this hub filter here. So you can essentially filter what is sent to this upstream. And so I've chosen to put the hub here because I have a development and production one in this same one. And this has to be in all lowercase. You can define it with uppercase characters, but it won't work. And then you wonder for about an hour kind of why am I not getting any messages. But yeah, that was a fun one. Let me check if I had anything else. Oh yeah, actually I do. I do have time as well, so I may as well show some code as well. Okay, now I'm going to make that a little bit bigger, and I'm going to close that. Okay, that is a lot better. So this is from the container app, so from the simulator's code, actually. And one of the things that it does is it does the device provisioning through the device provisioning service. And if we actually look at the definition for that, it's there. That's the whole code. And the big thing about that is, of course, the key that it is using here. And it's just a derived key from the master key plus a device ID. That's it. It's not complicated. And that's why I chose it for the demo. And essentially what it then returns you is the IoT Hub host name to connect to. And then we can connect and start sending stuff. Now, one of the big things that we do initially is that we get the device twin and we get the initial settings, essentially, and we update those as reported, so we confirm we've received them. Then we set this desired property update callback, which is essentially just, hey, call this function whenever there's changes to the twin. And we do the exact same thing again. And then we have our simulator where we are sending events, and sending events is pretty easy. It's just calling send event async on the device client. Notice that we were kind of having to do a little bit of data kind of transformation here because IoT Hub and Event Hub essentially just accept whatever bytes. So if you want to send in some other format than JSON, you can. And. And then we have, might as well just show you this one as well. So we have here we have our function that is receiving the location updates and updating the latest locations on the map and in the database as well. So it has an event hub trigger, so every time there's messages in the event hub, and it has a signal R output over there. And one of the big things that I'm also doing here is I'm accepting a batch of events at once, always. Because if you are not accepting a batch, then you are allowing functions to run your processors in parallel, essentially. So I didn't want that. I wanted to have control over it, so I just taken a batch of events at once. The batch size is actually reported to the dashboard. I'm actually going to check kind of how that looked like. So you can see there when I scaled up the container up, we slammed right into the default 100 batch size, essentially. So it did get it down as it started to get through the backlog, essentially. But typically you would see it doing like maybe 10 or so there at most. Also, usually you wouldn't be receiving events for the same device in the same batch because they're like every 5 to 10 minutes, right? The updates in the actual case, but I wanted to make it a bit more interesting here. But yeah, I'm not going to go too deep into the code here. You can check it out if you want. But one thing here is that we are returning from this function, this signal or message actions, with a bunch of parameters. And then those are received, if I can find it here. So the front end is using the Vue framework. I find it pretty nice to use. Okay, I've kind of forgotten where the callback for it is actually, but essentially it ends up here where we get those updates and do a bunch of math to figure out the speed and heading and stuff of the vehicles. There's one reason, by the way, why the app slows down quite a lot when you have a lot of events, because it's doing all that math in the browser, which is not the most optimal place to do it. Yeah, that's it. Anyone have any questions about the demo? Anything?
You promised us coordinate conversions beginning.
You
promised coordinate conversions.
We're getting to the coordinate systems. That's right here.
The architecture, was stream analytics ever a choice for like the middle part there?
Good question. So the question was a stream analytics choice? And you can absolutely use stream analytics as well. The only problem is that stream analytics doesn't have an output to SignalR. They don't have that. If you wanted to have a similar one, you could output to Power BI. They can have similar map views there as well. Well, not with like the custom graphics and all that for sure, but you can do that. But I wanted to do a little bit more data processing here as well, and I felt like the stream analytics wouldn't actually allow me to do that. Also storing the events, because I also have to detect kind of when there's an entry and an exit. Essentially, and wasn't sure how to do that with stream analytics. It might be possible though. Anything else? Good. So we can go to the exciting topic of coordinate systems. This is kind of important when you're working with location data. I think it's equivalent to knowing how time zones work if you work with time data, essentially, because it's a similar mess, essentially. And essentially, if you're not familiar with coordinates as a whole, I mean, you can just kind of hold your mouse, you can click and hold the location on Google Maps, and you can get the coordinates out of it, essentially. And so that's about 60 degrees latitude and 25 degrees longitude there. Not that Google tells you which one is which. I'm constantly having to check which one is which, actually. And now this one over here. One of my favorite pages on GitHub is falsehoods programmers believe about time. If you have never read it, I highly recommend it. It is hilarious and depressing at the same time. So I thought I'd make one about coordinate systems. The first one is there's one standard system that everyone uses. Okay, there's a handful of systems that everyone uses. The 0,0 location is standard. The first number is always longitude. The shape of the Earth is standard. Now, this one is like, okay, like seriously. This is the only like actually physical thing here. Like, really? Yes, really. The Earth's shape is part of the system. Like, cool. Coordinates are always measured in degrees. Continental drift never or always affects coordinates. The answer to that last one, by the way, and most of these as well, is it's the standard consultant answer. It depends. So if you're interested in checking out coordinate systems and kind of what they look like, you can check the EPSG registry, which stands for European Petroleum Survey Group. Now, this whole thing, like when I started looking into this doesn't really make sense. So an EPSG member created the registry in 1985, and it has never been maintained by EPSG since, but it's still called the EPSG registry. Cool. It's the global registry for coordinate systems, and you can see actually on the bottom there, when I took this screenshot, there were 13,419 systems.
Less than language models in Hugging Face.
Yeah, but still. So the reason for there being a lot of them is that they really are for different use cases. Also, some of them are more precise for certain locations. So there is kind of a reason for that. Like some of them are used for land survey and things like that. Now, if you can choose from these, I would recommend that you use these two. The first one is the one that Google Maps uses. It's the one GPS uses. It's the most common one. It's the one where you see coordinates like every time, essentially. Now, really luckily, these two are super common, essentially. Like in the business case as well, we did get lucky, and the source actually did use the first one, the EPSG 4326, and use that for data storage and calculations. Though that does come with a caveat. If the source data is in a different one, you may want to hold on to that original value as well. Because that 4326 is not perfect for certain things. It is the most general one, it's the one that everyone uses, and it's kind of convenient. And if you have data coming from different ones, then you'll have to most likely convert all of them to this one, essentially to do any kind of comparison between them. The second one, pseudo-Mercator, is there because we need another coordinate system for the map view. The map view is flat. As you know, the Earth is not flat, at least I hope you do. And so we need to somehow project the coordinates to that. So we need another system. And that's the one that, for example, Google Maps uses. It's the one Azure Maps uses. And the map SDK actually does the conversion for you. So you don't even need to do anything. But you may run into those coordinates in some cases, which is very confusing when you see the coordinate for this location is 52,000 something, and you're like, wait, what? Yeah, it's not the same system. So I also have a list of fun things that you will run into when working with spatial data. The first one is order of latitude and longitude. You may notice that I actually already flipped them once earlier in the slides. Sometimes you may have a .NET type called point, which takes longitude first. GeoJSON, the data format, also takes longitude first. Google Maps gives you latitude first. And the standard, in fact, is latitude first. Now, okay, so the point type I kind of get. It's an X and Y type. You know, it's not an actual spatial data. Longitude is the X coordinate. It makes sense. But GeoJSON, really? Why? So one funny thing about this is that if you flip them twice, or an even number of times, in your data processing pipeline, it ends up correct on the other end. So which,
How did you find that out?
So I found that out when all the locations on the map were correct, but somehow they were never entering the geofences. Like those events just didn't come up. And so they were the wrong way in there, but then got flipped when they got sent to the front end.
Two wrongs.
An even number of wrongs make a right in this case.
4 wrongs, right? 2.
Yes.
Gotta tell my wife this.
And so also another fun one is that, well, so you can scroll the map view, right? So you can go all the way to the east and you end up back where you started. Well, the coordinates don't wrap around. In fact, you actually they just increase the more you go to the east, or decrease the more you go to the west. So you can actually calculate how many rotations they've done. I'm not really sure what the use case is for this, but it is a feature in the map views. So you get like stuff like a longitude of 500 something, and it's like, well, that's not possible. They just go over the limit. Yeah, it's very funny.
Is it in the future then? Is it in the future then?
No, it's not in the future. That's not how time works.
I hope. I gotta read the falsehood programmers believe about time, I guess.
Yeah, you do. Another fun thing, in that projection, there's some locations that don't exist. So if you have locations around the South or North Pole, those are just not there. The reason for that, of course, is if you ever look at the full Mercator projection, the Antarctica is like bigger than Africa, which is like not true. It's just really, really stretched. So the map view people, they were like, yeah, we're not going to do that. We're not going to show this because it looks really weird. And who the hell needs to look at where stuff is in Antarctica? So, yeah. But if you're tracking like flights or something in your app, this can actually be a problem because we do have flights going over the North Pole, for example. So they would just vanish from your map view. So you're going to need to do something a little bit more special for that. Then some performance optimizations. One performance optimization that has already been done in the sample app is kind of a grid square system. So when we're sending these events, well, if some vehicle's location is updated in Japan, and I'm currently looking at Europe, I don't really care about that update event over there. So we might as well kind of subscribe only for the things that we're looking at. And that's what this system does. It essentially splits the map view into 1 kilometer by 1 degree by 1 degree squares, because it's a sphere. And then we add the SignalR connection to a SignalR group for each of those squares. And then we always, when we send an event, we send it to one of these groups. And so then only the ones who are actually looking at that will get it. Of course, what it means is that whenever you move the map view, we have to update those groups, essentially. But it does lower the amount of stuff coming to the browser. Now, Cosmos DB. Now, going into Cosmos DB, I really expected it to be a lot better option than SQL. And, well, it kind of is. Similar cost, Cosmos DB. Here, I think it was something like 1,000 RUs or 2,000 RUs in each of the 3 containers. It performed pretty well. It was also pretty consistent, like a lot more consistent than SQL. SQL has these like spikes where just for no reason, it's like, okay, I guess this query took 1 second, and that's fun. But that was most of the time, until we hit the RU limit. The problem with Event Hub processing is that it can be very bursty, and what happens when you slam a Cosmos DB really, really hard? It tells you, go away and try again. What the SDK does by default is that it's like, okay, sure, I'll wait a moment, and now try again. Now, what happens at this point is that because we have a constant load, events just keep piling up in the Event Hub while it's doing this. What happens? It takes another big batch and slams the Cosmos DB again. runs out of RUs, and this is now a loop of death. It will never recover unless you increase the RUs or decrease the load. There's just no way to recover from it. Or you start discarding events. That's the other option. Autoscale could help, could also be a bit costly.
In this case, of course, you could discard events because you don't maybe care about the
Yes.
vehicle's old position if you have the new one. But
That-
then you would
this is
have
correct.
to do processing to identify if
Yeah.
there's the new one in the pipeline,
Yeah.
and that would be its own job.
Yeah, so we could, for example, be like, okay, if it's like older than this much, then we could be like, okay, yeah, just discard it. And this is something that Stream Analytics also can do. For example, you can say that, okay, we just don't allow events older than this, essentially. But yeah, this is something that happened with Cosmos, and it just felt like it's not the best for this. Or you have to over-provision it, essentially. The other fun thing about this was that I tried to figure out what was causing this, and the metrics, looking in the portal, showed that I'm not hitting RU limits. The RUs were like 30%. I'm like, but I'm constantly seeing 429s from there, so obviously I'm hitting the RU limits. That's because the metrics are per minute average. And I'm hitting those RU limits on certain seconds, essentially, and it's not enough to change those metrics. So that was cool.
That's shit. That's shit.
Yeah, it is.
That's very bad.
It is bad, but of course, it was my mistake also for not looking at the other metric, which shows the amount of, rate-limited messages.
Yeah.
But still. The other performance optimization you can do here is to change the event hub partition count. That's because that sets your maximum parallelism. So essentially, you can only have one instance listening to each of the partitions. So if you have 4 partitions, you can have 4 functions app instances. Now, functions does the scaling automatically, which is nice. Now, one thing about it is that you really shouldn't just set the partition count to maximum of 32, because based on the measurements that I did and the testing, it adds overhead on the listener side. It also makes it scale out and in more often, which causes delays in processing as well. It just isn't worth it. And actually, for a lot of use cases, 4 partitions is more than enough. You're not going to hit those limits there. And in fact, the frequently asked questions for Event Hub says that it should be about, the kind of rule is that it would be about max 1 megabyte a second per partition, the throughput. So you can kind of calculate based on your event size and how many events you expect per second. And honestly, the only way to really find kind of what is best is through testing. The thing that sucks about this is that you can't change the partition count unless you're on premium or dedicated, where you can increase it. We can also do some optimizations in the Event Hub trigger in functions. One of them, which I don't think is going to really help a lot with constant load, is the prefetch count. So this is the amount of events that functions will fetch in the background while it's processing your batch. Yeah?
5 minutes.
5 minutes, thank you. But yeah, it's not really going to help if you have a constant load. Then we have this one, which kind of sets how aggressively functions scales, so you can have it scale out faster. Then we have this one, which is how often functions writes to storage the checkpoints, and essentially, because the events are not deleted from event hubs, so the client essentially has to keep track of where it's at in the partition, so it has to write this, and you can make it so that you write it less frequently. By default, it writes it after every batch. But I don't think this one helps that much. But what might help quite a lot in this case is to process events in parallel, especially if you're getting a lot of events per batch. This does lead to a higher database usage, higher all that, but it could be quite helpful. Then we have some bigger architecture changes that we could make. We could move the Event Hub processing to dedicated compute with also persistent connections to SignalR and not use the serverless mode. That would increased throughput by quite a lot because, doing the SignalR events over HTTP, not the most efficient thing. And if the number of geofences is low, as it is here, we could just keep all of them in memory and just do the geofence checks there instead of incurring I/O. We could also split the function up to several with their own storage accounts, but that's a pretty minor thing in my opinion. Okay, we have a few minutes, couple minutes for questions, if there are any.
If you have no questions, you can of course approach Jonas later. Let's have a 7-minute break, so
Yep.
the next speaker starts 5 minutes later than the schedule says. So
Yeah.
7 minutes, people. Thank you. Olet samassa jotain?
Ladies and gentlemen, we have on the stage Tom Kerkhoff.
You're way too enthusiastic.
Thank you, sir.
Good morning. So I am here to talk about. Is it on now? Yes. Okay. Good morning. I am here to talk about building a resilient API landscape and how Azure API management can help with that. So first of all, my name is Tom Kerkhoff. I work on Azure API management, so obviously I am biased. I work on the gateway itself. If you have any questions, you can reach out. If you have issues with the service, open a support ticket, please. I'm also a maintainer of Kubernetes event-driven autoscaling, a CNCF graduated project, and I am from Belgium. So we're going to talk about a couple of things today. First is we'll look at what an API management service is, very high level. We'll look at how you can improve your infrastructure, your applications. Then we're going to be a chaos monkey, which is basically what I do for a living, and then some questions for you to talk about. So every good thing starts with a disclaimer. We have two types of SKUs, SKU v1, SKU v2, which went GA a couple of weeks ago. I will primarily focus on v1. Sometimes I'll point out some things for SKU v2, but keep that in the back of your head. So, who has seen this slide before? Okay. So we talk a lot about the digitalization of companies and how APIs are the crucial part in that digitalization experience. Because without them, you cannot automate things, expose your data, etc. There's one problem in this chart, though. This is your single point of failure. If it doesn't work, or your digitalization is gone, and you're basically disconnected from all your partners, apps, and whatever. So this is very important, and this is where the resiliency part comes in, which basically means if something happens, what will happen, how will you react, and how will you recover and or mitigate from this? So this is something that usually comes up with customers after they noticed they didn't have it. So this is why I'm here, to help you think about it up front. Sometimes it's very simple, sometimes you need to make some design decisions. Now, if we look at API management, this is a nice marketing slide, but we integrate with a variety of services. We can expose a ton of your backends, but we have three main components. So at the top, we have the developer portal. That's basically a way for you to expose your APIs to your customers or teams internally, app builders, whatever, which gives them the documentation. They can have accounts, subscriptions, they can even try the APIs. In order to do that, you use the management plane, which is through ARM, where you basically define who's allowed access, which APIs do you have, how do you want to expose them, etc. And then we have the gateway, which is what I work on, which I typically call the heart of the service, because if that does not work, that's when they start calling us. This is of uttermost importance to us, that this one stays working regardless of the rest. If you cannot change your APIs, it is annoying, but you will not lose money. If the gateway is down, you're going to lose money. So we're also primarily going to focus on that one today. So how can you design for failure in your infrastructure for API management? So if you come back here, what this slide basically means is this single point of failure is the gateway in API management. If that one is down, you're going down. Like I mentioned, if Dev Portal is down, your partners will complain, but you will not lose any money. Well, maybe because of the partners, but indirectly. So this is where we need to go to Azure 101 first. What is Azure? Geographies. So in one geography, Azure will at least have one or more Azure regions, which is also the data boundary for that geography. And at least one region will have availability zones. There's also pairing. I believe pairing is not that important anymore. It's primarily about the next piece, which is in one region, there's going to be multiple facilities, multiple data centers, which are very close to each other. The new regions are striving to have availability zones in them. Hopefully 3, sometimes 2 are available based on capacity. But this is the important point, availability zones. If you can enable availability zones, always enable availability zones. Because if you spread your compute across the availability zones, that basically means if one physical facility has an outage, the other 2 availability zones will still be up and they work independently. So that's step 1. This also applies to VMs or any other Azure service. If you can use availability zones, always do it. So now coming back to API management, under the hood, we're just running compute for you. So if you create an API management service with 1 unit, what you actually get today is you get 2 machines that run both the control plane, gateway, and developer portal on each of these. There's an asterisk if you're using developer SKU. Who is using developer SKU? Not that many. Interesting. Who's using it? That's my next question. Who's using it in production? Nobody here. Thank you very much. There's a lot of people that do it. When I'm on call, it's always people running dev SKUs in production. So in dev SKU, you only get 1 machine, because that's also why you don't get an SLA. If we do an update, we're basically tearing down the machine, spinning up a new one. We cannot guarantee an SLA. Here we do. We add new machines, get rid of the old machines, etc. There is a DNS name for every service, obviously. And that's it. There's just 2 machines. We run everything on the same machine. And this is the first difference with SKU v2. SKU v2 has a multi-tenant control plane, meaning the control plane dev portal is also multi-tenant. Everything's multi-tenant except for the gateway. So if you spin up a SKU v2 service, you'll get a dedicated machine for the gateway, and the rest is basically shared with customers. This is only basic and standard SKU. We're working on premium. I honestly do not know what the model will be there, so stay tuned for that. So this is just 1 unit. Now, another feature we have is multi-region. I don't know where my map went, but there used to be this nice map. Okay, it's just a projector. So imagine here you should see America, here you should see Europe. So if I create one in Europe, you can add a secondary location in the same API management instance, which basically means you will take one of these units and deploy the same thing in the US so that you have lower latency. We're also sharing state across them. So that, for example, I believe it's for not rate limit, but quotas, that is being shared. Why am I saying this? Well, imagine I have my West Europe unit or multiple, and I add another one. There is a difference. You only get the gateway, which has pros and cons. So imagine West Europe goes down. You still use the control plane and the dev portal. So that is something to keep in mind. The primary reason we have this, though, is gateway latency and bringing them closer to your customers and the resiliency. So by doing this, at least, your gateway does not go down if we have a regional outage. So coming back to the host name, you get this nice host name, which actually is using Traffic Manager under the hood. Even if you use 1 unit, 1 region, there's always a Traffic Manager. And we have these regional DNS names for every regional deployment, which you can all access. So we have Traffic Manager out of the box, but if you decide that you want to help Probe itself use your own use your own Traffic Manager because you want to use a different policy, you can, by all means, do so. There is also a health endpoint that you can probe. So please do so if that helps you. So that is on the compute side. What I did not mention is we also support availability zones, which I'll show later. So please, if you can, enable it. Now, I hope at least you do not go straight to production. You hopefully have a production and a non-production or dev test production or whatever approach your company has. And then you have a couple of options. The first one is centralized API management, which means you create one API management instance. Dev, test, and prod is on that same API management instance, but you split the APIs on the service. That is something I would not do, because if a developer messes up and by accident changes a production API, then you will have a big issue. Also, if that service goes down, everything is down. So you can do it. I would personally not do it. Before I joined, I always used the second approach, which is the siloed API management. You create a service per environment, and then you basically treat them as separate environments on an Azure level as well. So if you do your rollouts, hopefully through automation, you can just reuse the same steps, and you have a guarantee that the end result will be the same. This is also why we have premium SKU and dev SKU. Dev SKU is almost identical to premium without SLA, with more limitations, but you can try these features in dev SKU at a lower cost. Yes?
Do you mind if I ask the audience how many use the siloed API management approach? Like, show of hands, how many of you use the siloed in your environment, your customer environment, whatever? Like,
not with API management, but in general.
Okay. Sorry for jumping in.
Nah, no worries. So this brings us to the next approach, which is the federated API management. So who heard about workspaces in API management? 3 people, 4 people, okay. We need to do some better work. So workspaces is basically a way to isolate your configuration. So your API specs, products, policies, everything basically. The missing point though is it all still runs on the same gateway. So if team 1 messes something up, they could potentially influence another team. If you want to have one API management instance, there's no isolation between environments. So something that is coming is runtime isolation. So what you will be able to do is take your workspace and basically get dedicated compute just for your workspace, only exposing those APIs, allowing you to split per environment, per division, whatever actually makes sense in your scenario. So this helps with that isolation, which also means if one gateway goes down, not everything goes down, and you have the resiliency between all of them. It will work like any other gateway we have today. It will just be a separate ARM resource that we are introducing for this. Who would like to have this today? Okay, Jonas. Thank you, Jonas. Okay.
He said please.
Sorry?
He said please.
Okay. So let me show a couple of things before I do. Oh, it finally worked. So let's see if it's in time for the next demo. I like to burn money with Azure load testing, but that's for later. So I have here an API management instance with a very low resolution. Okay. So what I have here is I created an API management instance in North Europe, which is a premium SKU, and the platform version is STV2. If you go home and you have an API management instance that says STV1, please cancel your weekend plans and migrate to STV2. Do it on Monday, that's okay, but we're shut. Actually, deprecation passes end of August because we're getting rid of cloud services. So you really need to start moving, but okay, I have STV2 here. Basically, this means the gateway runs on VMSS under the covers. So Let me show the creation experience, because there is an interesting part there, which I skipped. And you need to rush for time. So if you create a new API management instance, there is two things to note. It defaults to standard v2, which now has an SLA because it is GA, and I can just pick how many units I want. But we're talking here about premium, so notice what changes. In premium, I get to choose which availability zone I want to use, and then depending on the units, I can add more. Note that you didn't see this for standard v2 though, because in in v2 SKUs, we're using availability zones by default. So if you use 1 unit, we're going to spin them in 1 zone. If you have 3 units, it's going to go to 3 zones. So you don't have to worry about it. In v1 though, you need to choose it because it was not there from the get-go. So please do so if you can. Okay, going back to this instance I have. So imagine I want to go to multiple regions. We have this location section here where basically you can add gateways in various regions. It's the same approach. The capacity, you assign a bunch of units, and then you can pick the availability zones. In this case, I didn't add availability zones, so I could just say, let's go to these two, click apply. Actually, I can click apply and then hit save, and it's going to update everything. So if you want to go to a new region, this is the place where you want to go and scale out basically into a different region. Now, how do you know if you should go to another region if resiliency is not the reason? So this is where application insights comes in and is very handy, where you can use the availability checks to see how your APIs are doing. So for example, I've set this up here, and you can see, apart from a couple of outliners, everything is pretty fast. But once you start zooming in, you can see that the majority is below 1 second, but some of them are above 1 second. So above 1 second is still fairly okay, but you can see that this is always Brazil. I think Canada, Australia is also here. So if you have a very big customer base there, this is also a way to basically measure if it would be useful to deploy a gateway there so that they can go to the local gateway, which also means you're going into the Azure backbone faster. So we're just a proxy. We take the request and send it to the backend. If your backend is in Azure, that's also going to improve the latency there. Okay, so second thing I showed was the regional host name. So I can just probe this, for example. Note the North Europe 01 here. That is basically all you need to add along with regional. So if you, and this is the help probe, you can use that, by the way. So if you forget this name, like I do, if you do a simple NS lookup on the service name, you'll also see that it's going to be listed here. That means I can also, and I'm lazy, so let me just do this. You can also just talk to the Southeast Asia one if you want. So if you want to set up your own traffic routing, you can do that. If you want to do health monitoring on the regional gateway level, you can do that. Let me have a look at my cheat sheet here. So I showed this. Yeah, so capacity. Capacity is basically a way to measure if the gateway can keep up. And apparently what not a lot of people know is that Azure Monitor has the capability of splitting metrics. So for example, here you can see, our service is at 34%. So you can basically split and then see, okay, out of that total capacity, the majority was in North Europe, so Southeast Asia is fine. So that can also be a way to measure, okay, of all the locations we have, North Europe is like the bottleneck. There's two ways to fix that. One is you can consider adding another gateway in another region that's closer to distribute the load. Because at this point, if North Europe goes down, you're going to lose the majority of your traffic, right? So going to West Europe, France, maybe not West Europe, that's full, France Central, UK, whatever that works with regulation, that can help. Or we have integration with Azure Monitor Autoscale. And this is why I wanted this one to run faster, this load test. But I'll show that later on. What that basically allows you to do is ask Azure Monitor to say, when capacity goes above 70%, start scaling out. When it goes below 40, please scale in. This sounds super simple, but a lot of people don't know this is baked in, and you don't have to worry about it. Now, in this case, I did the simple approach, but same applies here. You can also do this on a regional basis. If you do not do this, I believe it's going to scale out the primary gateway by default, which is not always the good mitigation if, in my case, Southeast Asia would be overwhelmed. So you may want to set up auto-scaling on a regional basis. And then you can basically use the Azure Monitor history to also check when you were scaling out your units based on the load. OK. So another thing to think about is if you're using external caching, which I did not set up, you may also want to consider adding a cache in a region, because otherwise that's not going to work very well. And then lastly, while we do have a managed service, you can also use our self-hosted gateway, which is this guy, which basically allows you to deploy our gateway. No, don't use YAML. Deploy the gateway to Kubernetes, to Azure Container Apps, to other clouds, so that assume Azure has a total outage. I hope it will not happen, but assume you still have a gateway running on AWS, GCP, or you have workloads running there. You can use our gateway, deploy it there, expose the same configuration. Another way of resiliency, but yeah. Any questions on this part? OK, that's easy. Moving forward, so I showed the regional usage. I did not show this. So application map and application insights is also a very good integration to understand how your traffic flows, latency, error rate, etc. So here you can see the top is my Southeast Asia deployment. The bottom is my North Europe deployment. You can see how many requests goes where, and then how many go to which backend. Very important. While the gateway may be resilient, and I can have a gateway in every region of Azure, if you're still using the same backend in one region, you have a problem. Because if that backend in West Europe goes down, everything goes down anyway. So that is something to think about. I'll come back to that in a second. Now, to recap, use availability zones. SKU-v2 has them built in. SKU-v1, you need to use a premium to use availability zones. And also, you need multiple zones to get a 99.99% SLA. Otherwise, I think it is 99.95%. So if that matters for you, also check the documentation. Auto-scaling, set it up. Make sure to set a maximum replica as well. Very important. Ask me how I know. Multi-region can be important to bring gateway closer to your customers to make sure that your total instance does not go down in case of a regional outage, and you are faster in the backbone. Chaos testing, I am saving that for last. But this is also an important point to think about. Now, apps and backends. So imagine you have a backend, let's say app service, and you want to use the new shiny, let's say, containers. You're migrating to ACA, so you need to basically route your traffic to the new backend, do experiments, etc. So this used to be a very painful thing that you had to do through policies. Now we have actually a load balancer built in. So the idea is that you create a resource which we call a backend, which now has a type pool. And all it does is it basically points to two different backends in the service. So in this case, I'm very creative. I'm routing traffic to Google and Bing. And in this case, I did not specify anything, so it's going to do simple round robin. Since build, we announced two new approaches, which is priority-based routing and weighted routing. So now you can also more influence what that looks like. The second thing we did was introduce a backend. Both of them are GA since build. We've had them for half a year, I think, so that if your backend is having issues, you can open the circuit on the gateway and don't even bother sending it through because you know it's broken, it's overwhelmed, so we'll allow it some time to recover. That's the idea. You can use percentage or account-based, I believe, and we're working to add synchronization across instance. So I mentioned we have one unit, which is 2 machines. So if you are lucky, it's going to allow a couple of more calls because the synchronization is not there yet. Okay, so let me show this quickly. So I have this backend here because it's almost lunch, which just returns different flavors of bacon. So I'm going to use this. It's just returning a simple list with payloads. And if I go to APIs, oops. I have a bacon API here with just one operation, get bacon. So if I go to Postman, I actually have this set up. So this is my very creative demo app. It gives 5 flavors of bacon. Apparently these are a thing. Never heard about them. So there's a couple of headers here. So I added upstream URL, I added a polar bear, the region of the gateway, the name of the service, the ID of the gateway, and if it is managed or not. These are all basically baked-in information you can use in the policies. Why is this useful? I'll show that at the end, but in this case, the upstream URL is important to show. So here it goes to Wonderful Beach, which is basically one of Container App's host names. And this is because I believe this is the default, which you can see here. I don't know why Portal's so slow, but okay. That is the default. So what we'll do now is we will make this bigger because it's small. Jesus Christ. Okay. Of course, we have a co-pilot here. No, I'll save that for later. No, go away. Okay, so in the past, when you wanted to do load balancing, this is what you had to do. Okay, it's a little bit too big. So you had to be very creative and basically say, give me a random number between on 1 and 2, because I have 2 backends to load balance across. And then the default upstream URL is the one defined on the API. So then we have a choose that basically says, well, if this generated ID is 1, let's assume it's the default. If it is 2, then change the backend to this new URL to route to. And if we messed up the policy and there is another value because we updated it here but not here, then let's return a 500. And then all we do is we set we use the set backend policy, and then we fill in the host the URL of the new upstream. This is very cumbersome. You need to know how this works. So what we did was we have this pool now that I mentioned, where in my case I have 2 backends already, Contoso. Actually, the names do not match anymore, but a monolithic approach and then a new approach. And instead of sending traffic to these directly, we're going to set the backend to this new one, which is called Products Load Balancer. So now the policy just looks like this, which is a lot better. So let's take this And now I remember, I actually need to use my other API, not the bacon one. So let's do that quickly. So this guy here still has the policy. Interesting. I didn't clean up. So it already has the policy now. So what we will do is we will basically request, we will first make the portal a bit bigger, and then we will send a request, and then see that it was calling the monolith on app service, and then next monolith, container apps. The portal is not so slow today. App service. So you can see it's basically doing the round robin for us. Now, this is very simple, but what if it goes wrong? We have this capability called API Inspector. So if you click trace, and it did not ask me for if it's allowed. Interesting. Okay, if you use trace, you basically can get a trace. If the portal's, okay, here we go. You can get a trace of the request. I typically call this the request's life cycle. So if you need to debug a request, this is where you need to go, because it shows the request that was made, and then it goes through every single step. So it was able to resolve the operation that was called. It was then checking course is not used. Then it sees it needs to set the backend, which is this name of type pool. That one then forwards it to this one because it resolved it this way, changes the backend. This was the old one, this is the new one, there's no proxy. Then it shows the request to the effective backend. Then the response comes back with an OK and headers, etc., etc. So the more policies you add, this is very useful. Also, if you open a support ticket, this is going to increase the time to mitigation or resolution, because this helps a lot for us. We do not have access to this. So, and then here you can see that it added all the headers. Now, let's break stuff. This is what I prefer. What the hell?
You said let's break.
Yeah, exactly. What the hell? See, that's what I said. I'm a chaos monkey for a living. Okay, so this is where I need to bake an API. So I send a request, which is basically here, going to this container app. It will always give me the bacon. Now, imagine your backend is failing. So in this case, I just introduced some chaos. And now it starts giving me 500s all the time. So this is not very useful. I'm just clicking the button here, but imagine you're getting tens of thousands or hundreds of thousands requests. You don't want to keep overloading this backend. So this is where this circuit breaker comes in. Instead of sending it through, basically just open the circuit. And here I'm basically using a backend that says as soon as there's 5 failures in 1 minute, which means one of these status codes, then open the circuit for 1 minute. And same applies here, actually, let me copy this. If you apply this policy, which again, all it does is set the backend service to this circuit breaker. It will open the circuit after 5. And here is another example of the valuable policy expressions we have. You can get information to all the errors that a request has. So in this case, it's circuit breaker. If this would be your web app, it will also produce an error. Or in case of a policy, this is how you can use it. I'm sending it to the client. No, don't do this. Send this to your telemetry or whatever, so you have insights. But I'll basically apply this. In case somebody wonders, yes, you can combine load balancer with circuit breaker, I believe. Read the documentation. If we do not, we definitely will. But you can basically mix and match all of these. Portal's having a very bad day, so I need to talk more. Okay, let's see if it already, this is not going well. Okay, so, okay, oh, of course, when I stop testing, it works. So, I'm doing a few calls. Boom, 5th call succeeded, 6th one said 503, service unavailable. This is the circuit breaker kicking in, which you can also see here in this error information that I started propagating. So this is a simple way to do it. And just to prove the point, I like Azure load testing, so I simulated a scenario here yesterday where how many did we send? 440,000 requests, and it was always calling this one where it creates the 500. So it simulates a 500, it causes a 500 on the back end. But note that we only got 1K 500s. The majority was 503s because I applied the circuit breaker. So what was happening was we get the 500s, circuit breaker opens for a minute, which creates all the 503s. We check if the health is fine by closing the circuit again. We keep on getting the 503s, so it opens it again. Now this is a load test. I could not change the request, but imagine in the middle, the backend was suddenly healthy. You would see that the circuit breaker closes again and all errors are gone because it sends it through now. But yeah, like, out of the 440K requests, we were able to deflect 437K from the backend, which hopefully allowed it to come back. That's the point I wanted to make. Okay. So, what do people do if the backend is slow? Because they always read that retries are wonderful, so they use a retry policy and just retry it and retry, which basically causes downtime on your backend. Who had this before? I already saw Saka laughing, I knew. Okay, so this is a natural mistake. So that is why consider using these circuit breakers by default, because this is not where you want to be with production. So there's another fun exercise, is what I call the mystery of the capacity murder. So this is based on a live scenario I had with a large reinsurer when I was still a consultant. And we had a partner that was very enthusiastic. So this is why my load test should have started earlier, not during the talk, but let's see. So what I did here was, let me take a step back. So this is Azure load testing. Who has heard about it before? Okay, that's what I like to hear. They did a big update at build, and now you can run one load test with virtual users from multiple regions. So again, if you want to test how your gateway reacts across the world, and you have a big wallet, this is where you can go. I'm joking about the wallet. You can choose how many users you want to use, but I always exaggerate, because why not? So I started one here that has it's simulating 4,000 virtual users, and I'm hoping to break the gateway. Shouldn't, but let's see. I'm breaking the backend, yay. Oh, actually, it's the 503, so this is the circuit breaker that I applied. Yay. So why is throughput so low? Oh, it's still ramping up, yeah. We're at 4K virtual users. With machines in 2 regions, and apparently they're not displaying this. Can you split? No. Oh, here. So out of these, 3K is from West Europe, and then the other one is oh, now it shows it. So here you can see the growth, you can see latency. You can see latency is very bad, so I guess I messed up this load test while doing it on stage. Not recommended. So the goal I wanted to have is, let me fall back. Don't change your demo right before this presentation. So I wanted to have something like this. It was not generating enough capacity, but imagine your API management instance this capacity is going like this. Oh, it went up. Not as high as I wanted, but imagine your capacity goes up. And you are, not in this case, but at 100%. What do? Why are you at 100%? There's a couple of things that you can do. First of all, mitigate the issue. So mitigation is fairly simple. Scale out. Make sure you get more capacity. So this is, again, where you should use this splitting to see which one is overwhelmed, scale that one out, etc. Second of all, make sure people cannot abuse your system. And abuse can be very simple. So in this case, I have, actually I'm not going to show it, but I have simulated a scenario where somebody is generating a ton of requests, which you will also see, or like natural reaction is capacity is high, so we must get a lot of requests, right? Hopefully, otherwise you have another problem. So here we see this sudden increase in all these requests. But why? It was fairly stable before. So how come? Same here is you can add some of these splitting, like what was the response time. Everything was fine, starting to get overwhelmed, but we still don't know. So if the load test would be running, what I would recommend is create a rate limit policy so that you prevent people from continuing to overflow. At this point, we don't know what's causing this, but let's just add an additional safety measure, either on a given API, but in this case, we don't know where it's coming from. So what you can do here is, actually, let's try this. Generate me a rate limiting policy to block requests to only allow 5 requests per minute. It's a stupid number, but just because then it becomes demoable. So let's see what it comes up with. But we have this rate limit policy that basically allows you to say X amount of requests in Y amount of time. And we also have rate limit by key, which means instead of having a global rate limit, you can define what the key is to rate limit on. Very common scenario, subscription key or API key, so that you can do it on an individual API key. I am not so patient, so I will just, oh, where did it go? Okay, I offended Copilot, sorry.
Maybe it's applied already.
No, it doesn't apply. So now it's going to, okay, interesting. Okay, let's do it ourselves. So I have here a very simple policy where we're going to rate limit, in this case, we don't have much time, nor load testing. So we're going to start blocking requests once they do 5 calls in 60 minutes based on the user's subscription ID. So, actually, let me just copy this line. So again, if the load testing would work, we would almost instantly see this in action. Oh, it cannot assist with my sorry. Okay. Interesting. What? Oh, I misapplied it. This demo is not going well. Okay. So I'm applying it. I applied it on the all API scope because we have no idea where it's coming from, who's doing it, etc. So I'm going back here. And because I applied it on the all API scope, this policy is going to kick in even before the circuit breaker. So, Jesus Christ. Let's start hitting this button. And then as soon as I do a couple of calls when it is applied, see, so we get a 429 issues mitigated, so we can start doing the investigation. Actually, I don't know if this guy is still running. So this is the old one. Although this one was broken, we will now also see that it will start showing some 49s eventually. Oh, whatever, this is dead in the water. So now that we have mitigated it, how do we know what was going on? So there's a couple of things that we provide you. So first of all is the API analytics. So API analytics is a very powerful way to, hence the name, analyze what's going on. So you can get a timeline, response time, etc. if you care about that. Here you can also see the latency per geography. So again, multiple units, different regions. This is the information you can use. And then I will go here. So you can have the same information on API, operation, product, subscription, user request scope. I don't know what's going on. So, how's the weather today? Okay, here we go. So in this case, you can see that all the requests in this case came from a subscription called Malicious, which did 8 million requests, of which 18,000 were unauthorized. Why were they unauthorized? Interesting. I guess that's the messed up load test. And now that we have mitigated the issue, we know that this person was malicious. So a couple of things you could do. You can revoke his subscription. You can rotate the key on his subscription because maybe his API key got leaked, etc. But now you know who did it, and you can contact them. This is a true story. One person had this at a client I used to work with, and instead of polling every 1 minute, they decided to do it every second. So we said, please stop, and they didn't do it, so we made them do it. Now, this approach, hence the name, is classic. This is not the future. I don't know if it's deprecated, but we have this new approach here, which offers the same thing. And why is this interesting? It is built on top of log analytics workspaces. So basically that means we give you the data, we give you this workbook by default, but you can tweak it. So a common ask we get is how do we monetize our APIs? Well, you can use this and basically tweak it so that based on the user, you know which customer it is. You can then add your prices, etc., to those workbooks. So it's same information that you have here. Okay, did it kick in here? Oh yes, at least it worked here, 429. So now this test is also getting blocked. What I was not able to show, because this one did not work, is that the auto-scaling would have kicked in. So let's check, but I'm not expecting that to work. No, capacity was not high enough. Anyway, you get the idea. So you can first mitigate, check metrics, apply policies, and then investigate further what was going on. So we used load balancer to route traffic. That is not the only approach. We also have context properties for the gateway that I showed. And why is that important? If you have multiple gateways, you may want to change the backend to the regionalized gateway. So if you have one in West Europe and Southeast Asia, you want to call the Southeast Asia API when you're in Southeast Asia. So you can do deployment.region, for example. We also have the gateway ID, gateway instance name if you're using self-hosted, and also an indication if it is a managed gateway or not. Again, if you're using self-hosted, your routing will be different, so then you can use all of that. Or you can set up your own traffic manager, both before API management or after. So a traffic manager can be a backend hostname as well. So, of course, AI. Just using AI here as an example to showcase why these things are important, where typically you start with this one app, in this case, an intelligent app, and you have this one backend. But then you start to become more successful, and you have a lot more traffic to this one backend. So people always ask me, when do you introduce API management? I always tell them at the beginning, the very first beginning, here, because changing this situation is a lot easier rather than in this situation, because you need to migrate more apps and clients and whatever. So in this case, if you have to kind of do load balancing or whatever, this is hard because you rely on a third-party service. So you don't know who's using it or whatever. So that's where a gateway always comes in, be it a Gen AI gateway with AI capabilities, but because of having the gateway in the middle, you can do all of these things for you and offload from the backend usually. So in this case, for load balancer and circuit breaker, in terms of Azure AI or any backend, you can just shift all the traffic there. Okay, to summarize apps and backends, I don't know how much time I have left, probably over, but 4 main things. Prevent abuse, so rate limit, quotas, etc. are very important. Protect your backends. Use circuit breaker to protect them on so that they can basically recover from failure. Use load balancing in case you need to, and use retries, but use them very carefully. Let me check time. Okay, I need to hurry. So unleashing your inner chaos monkey. So Netflix coined the term chaos monkey because they started shutting down VMs in production randomly to check the resiliency of the platform. Kudos to them in terms of having the balls to do that. So this has started to become more of a term. We do not integrate with Azure Chaos Studio, but that is an Azure service where you can do this basically as a platform as a service. However, we have some capabilities that can help you. For example, using Azure load testing is a very good way to start. Throw a lot of load at it and see what happens. We get a lot of questions on how much capacity or units do I need to have X requests per second, or which regions do I need to go to? Should I go to multiple regions or just have multiple units in one region, which was literally a question yesterday. Our answer is always measure it yourself, because it is very customer specific depending on policies you have, infrastructure you have, networking you have. Now, the interesting thing is not only how will the gateway scale or react, but primarily how does your backend react. I work on the self-hosted gateway along with the managed. For self-hosted gateway, this is a very big topic. They're telling me self-hosted gateway is slow, but they forget that the backend is also part of the request cycle. So that typically also is the problem in these cases. And just to give an idea, we have automated benchmarking set up for all our gateways. And we've set up this backend, which we call Godzilla. 1 minute, okay. We have set up this backend called Godzilla, which has 1 million requests per second to make sure that we do not have the backend as a problem. So rule that out. But the fun stuff is you can simulate an outage because you can basically shut down the gateway in every region, not every region, in all regions except for one. So there is a flag in ARM which is called literally disable gateway. If you turn it on, we're not going to start the process. So there's nothing going to handle the request, which means all traffic will go to another region. So I have half a minute now. Instead of answering these questions, if you're using API management, think about all of these. What happens? How will you know them? Always apply rate limit by default. Be careful with health probes as well. They're very noisy. And one I will answer. If your primary region goes down, your control plane goes down, which means you cannot mitigate anything. Keep that in mind. So in case you want to shift traffic to another region, you cannot apply policies. So make sure to think about traffic management upfront. And here are some links if you want to learn more, but thank you very much.
Let's eat! Yeah!
All right. Hope everybody had a great lunch. Next up, we'll continue with our technical presentations here with Thomas speaking about functions and function triggers. Go ahead. Let's give Thomas a big hand.
Thank you. Welcome, everyone. My name is Thomas. I will ask to start with the second part for your convenience. I'm a staff engineer. Is that better? Is the mic working at all? Can we check the mic? It doesn't seem to be working, although this is not on mute, so I don't know how to turn it on. Technology just beat me.
Seem to be turning on.
Is there like a different one? Maybe this is out of batteries? Is that better? No. Yes. It's not open. I want this one. Five-minute technical break.
Try again. How about that? All right. Yeah.
So let me put that on. That's not easy. Help me with this a little bit.
Yeah. So just next.
Okay.
And maybe a bit lower.
I need to grab the second one. Yeah. Okay, is this good? Yes. Sounds good. Yes. Finally. Yeah. Yeah. Okay, so after this short break, let me start again. My name is Tomasz. I'm a staff plus engineer / global product architect at Software One. I've been to our industry for quite a few years already, and during that time, I have built or helped others to build various solutions for various industries on various technologies. And today, together with you, I want to dig into one of those technologies, Azure Functions. From my experience, Azure Functions is actually a very interesting subject of discussions. I have chatted with a lot of people about Azure Functions, and majority of them I can divide in two groups. One is people who, after like a first serious project with Azure Functions, would say, I like it, it's fun, I want to use it again. And the other group is more like, I don't feel it, it feels off, I don't know if I want to use it. What is funny is that both of those groups, very often they justify their position with the same statement. It feels magical, right? And personally, I take such a statement as a problem, right? We are building software-based solutions. They should be based on technology, not magic. If we are basing them on magic, we are setting ourselves some problems, issues, etc. That doesn't mean I want to tell you not to use Azure Functions. Quite the contrary. I want to look under the hood together with you, so whenever you will be using them, it's no longer magic. If you need, you can go deeper, you understand what is happening. Because personally, I like Azure Functions quite a lot. I think it's a very nice service. It fits certain usage scenarios very well. Not all of them. Nothing is for everything. So I didn't say that. It has nice features, nice capabilities. It's constantly evolving. To be honest, I even like the logo, right? The logo of Azure Functions is one of those very few logos in Azure that are actually telling you what the service wants to do for you. Because what Azure Functions wants to do for us, they want to enable us to focus on the business code, the code that is actually important for our organization or clients, right? The code that we are actually getting paid for. And it promises that we'll run that code in the results of all the other events happening in the system, right? Well, that's, of course, a simplification. Our code is never that simple. Our code requires some additional data on the input. It will produce some data. And Azure Functions wants to deal with that as well. Azure Functions wants to take away the integration responsibility from us, allow us to focus on the business code. And that's the part that often feels magical to developers. Because we are developers, we are so accustomed to write integration code. Sometimes we even write more integration code than the business code. Sometimes it's even more complex than the business code. So the moment it goes away, this is some kind of sorcery, right? I need to do that very hard, important thing. So today I want to go deep under the hood together with you to see how Azure Functions is tackling that complexity for us. Because it's sitting in a very specific case. That's the responsibility of triggers and bindings, right? Those are doing that integration part for us. And if we would have like hallway track conversation about Azure Functions, somebody would probably say there is a lot of integration, a lot of different services that you can use. The truth is that Azure Functions, as they are, deployed in Azure, run locally in containers, they support only two things, HTTP and timers. That's all that is. All the other integrations that you may know, Cosmos DB, Service Bus, different kinds of storage, even durable functions, those are all extensions. You get those extensions into your applications, depending on the language, that's either like direct reference to a package in .NET or some definition in host.json in different languages, right? So in order to truly understand triggers and bindings, we need to understand those extensions. And you can probably already guess, there is quite a few things in there because that rectangle is quite big. That means I can put a lot of smaller rectangles in there. And this is exactly what you're going to do. I'm going to start with the stuff we have already named, bindings and triggers, right? This is the stuff that manifests itself outside. If we are .NET developers, we interact with this directly. We have attributes coming from those packages. We apply them to parameters, return values. This is how things works. If you are working with different languages, in Java we have annotations, we have definitions in functions JSON. They all boil to the same concept, representing that attribute. And the core of that integration responsibility hides in those two components. So how they look inside of Azure Functions? Let's start with bindings. Bindings are responsible for integrating data on the input and on the output. Internally, they are represented by something called binding rule. And that's just a mapping container. It maps that attribute that represents the binding outside with different components responsible for integration. That can be either value binder. Value binder is responsible for in or in and out integrations. And those in and out ones are something that you are very unlikely to see, right? This is basically heritage of programming languages that generally support in and out parameters, but we no longer use them, right? That often, at least. And in Azure Functions, you can do the same thing. You can get a value on the input, modify it during the execution of the function, and it will be updated on the output when you're finishing your function. But generally, we don't do that anymore, right? We want our code to be clear, readable, so we want to return our data explicitly. And there is a separate component for that, asynchronous collector. And basically, from like bindings, from input and output perspective, this is all there is. Nothing more. 4 rectangles, 3 arrows, right? Looks simple, because it's a diagram, right? And diagrams are for architects, so they can simplify things, right? Later developers come, they have to implement something, and problems arise, right? This is why it's the best to be a like hands-on architect. You can first lie to yourself with a diagram, then you sit together with the team, you suffer the problems, right? So that's perfect. So in order to understand what is actually happening there, we have to take a look at the code. The code has to be .NET C#. That's the language of extensions. We're not going to be caring for any specific like syntax details. We care about the concepts that the code is expressing. Let's start with that attribute, because that's the entry point. And usually with the attribute, nobody is expecting any kind of problems, some strange things, right? Because attribute is simple. You can decide where to apply it, parameters, return values, and it has properties. That's all what there is. Those properties are what we know, right? This is where we provide values when we are configuring our functions, writing definitions. The trick is that the moment you start looking inside Azure Functions because you want to understand something, you can notice that this attribute is getting to use in various different ways, which doesn't make sense, at least at the first glance. Because Azure Functions is seemingly transforming that attribute depending on the context that you are in. And there are three main contexts in Azure Functions. The global one, that's the one that binding rule exists in, right? All the definitions, etc. Function definition one, that's the one we as developers interact the most. We are defining our functions, what they are supposed to do, how they are supposed to work. And the invocation context, the one which is actually most important for the Azure Functions, and we usually doesn't see it. And the difference is that, as in the definition context, we are providing some values here, we will notice that in the invocation context, those values are completely different. And that's the result of those different decorations on those properties. If we have an upsetting decorated property in Azure Functions, that means that during definition you have probably provided some kind of a key that reaches to settings, etc. If you look at the code that is touching this parameter in the invocation context, there will be ready to use value. Azure Functions will pull that for you. The same for the auto-resolve one. In the definition context, you would usually put an expression there. A typical example, you have an HTTP trigger, and you have an additional input binding that, let's say, is grabbing something from the database, and you want that item to be grabbed by an ID from that URL. So you write an expression that is parsing that URL. And Azure Functions, for the invocation context, is automatically calculating that. So there is a ready-to-use value. And that's actually important to know if you want to look deeper, understand deeper, because that is reflected in all those integration components where it's hiding that logic that you are interested in. Let's take a look at value binder. As I said, it's responsible for in or in and out integration. It has two methods, get value, set value. Makes sense. What might not make sense for you, at least when you look the first time at it, that there are no parameters here. I mean, there is a value for that set value, but nothing about the context. So how does it know which functions it's getting value for? Well, the answer is that value binders always live in that third context, the invocation context. They are created for a specific invocation. And that has consequences, because that means there can be quite a lot instances of them, as many as parallel executions of the functions. So they contribute to resources consumption. They also contribute to latency, right? Because they have to be created, destroyed per every invocation. So they have to be truly lightweight. All the state, so all those values from configuration, from option, this attribute, any hard processing or state management, like any complicated logic, connection pooling, caching, it has to happen outside. If it would be happening here, functions will be 10 times slower or even worse, right? So this is why we have that important third context to actually be able to inject that very quickly when this is constructed. The same comes from asynchronous collector. In fact, you can experience that firsthand if we are .NET developers, because in case of .NET, you can ask for a parameter of type of asynchronous collector. You will have direct access to that add method, right? This is usually how you return multiple values from your functions. But if you are not doing that, you are just returning a value or you're using a different language, Azure Functions will create this for you, call that add method. So whenever you are interested of how Azure Functions is integrating your output data, just find that asynchronous collector, go to the add method. It may have different levels of complexity. If it's just a queue under the hood, then probably just inserting an item. If it's a database, then integrations with databases, usually they can do insert, update, and create structures. Containers, tables, they do that. So whenever you want to actually know what they are doing, how they are doing, what is the logic, just find that method, take a look. It's on GitHub, right? So now we have a gap, right? We have those components which are responsible for integration, and they are in the invocation context. And you have that binding rule, which is global. And you have arrow, the greatest simplification in all of the designs, right? Arrow. What that arrow must be to actually be able to go from that binding rule to something that is being created per every invocation of the function, right? That arrows must represent something that is able to create a significant amount of those objects quickly. And we have a solution for that, a pattern for that, factories, right? So what those arrows actually represent are factories. What is actually registered with the binding rule is factories. And there are multiple ways of registering that factories, and there are two important ones. One is a generic factory. And it's a nice factory because it's enclosed in a type, so there's a place to separate logic, encapsulate state, do some testing, but it comes with a price. The registration for a generic factory is that first one, bind to input, requires providing a generic type parameter. And Azure Functions will use that type parameter to actually validate if the binding can be used for a specific function definition. That means this parameter provided here must somehow match to the parameter used on the function. If they don't match, matching is a hard word, we're going to get into details how they can match, then Azure Functions will say, I cannot start this function, the binding doesn't match the definition. And this is often a very serious limitation, especially if our input is something that can return JSON. So extensions author would like to be helpful for the developers, be able to basically deserialize to anything. So in that case, this is where that second way of registering factories comes in, something that doesn't have no limitation, bind to value provider in this case. We are getting a lot of flexibility for a price of complexity and simplicity at the same time, because that second type of factory is just methods, and methods are not perfect to represent something potentially complex, because first question is always, where did the extension author put that method? And there is no rule for that, so finding it may be a little bit harder. Also, methods are not great for like encapsulating state, right? That's a problem. Encapsulating logic, testing if they are private somewhere, right? And those methods will be more complex because they have to deal with that support of multiple types. So they usually contain some reflection, right? That's the .NET mechanisms for that. And that's hard to interpret. That's actually stopping us from getting where we want to the actual integration code. Luckily, we don't have this problem with the asynchronous collectors. They support only that generic registration. The trick is the first time you will take a look at this factory, you will be surprised because it's a converter. That's a typical factory interface, right? But it does the same thing, roughly. We have the type of the parameter. That's the generic type. We have that attribute in the input, in the invocation state, and it is supposed to produce an asynchronous collector as a result of conversion. Unusual interface, but works as a factory. But we have now this problem of limiting that type that can be used by a function. And Azure Functions has a, let's say, very tricky solution for that. As you can see on that snippet, and all those snippets that are coming from a custom extension for RefingDB, and I doubt you ever used RefingDB. Anybody did? As expected. I once worked in a project when we were moving some stuff to the cloud, and RefingDB was crucial, and it was nice for running in containers, and we write a custom extension for it to be able to use Azure Functions with it. And you will probably be guessing that this RefingDB open type, it's something to do with RefingDB, right? The name suggests that. The trick is that the important part of the name is the second half, open type. Open type is something very specific in WebJobs SDK and in Azure Functions SDK, because Azure Functions are built on top of WebJobs, SDK are built on top of each other. Open type is something that in certain scenarios for Azure Functions means T at runtime, generic, anything, basically. If Azure Functions sees open type, fine, I can think anything. And you can further deliver from open type to narrow that. There's one ready-to-use option, opentype.poco, and it's not no longer anything. It has to be an object with properties, and extension authors are delivering further, building logical conditions for those types. So if an extension author was able to express the requirement for the type supported by the binding in a logical way, it will be here. And Azure Functions will evaluate that isMatch method when it's reading the definitions of the functions. If it returns false, Azure Functions cannot start this function because the definition doesn't match the binding. Right? That's the almost exact error message. If it's true, fine. We are assuming that the extension author know what he was doing. It will work, right? So those concepts, those value binders, asynchronous collectors, those factories, this open type solution, let's call it like this. They are what actually makes up bindings. If you understand those concepts, you can actually go to GitHub, grab any extension, read it code, you will understand what is happening under the hood. But bindings are a little bit less important. I mean, I don't want to diminish them. They are very important. But what is more important is triggers, right? If there wouldn't be a binding for a specific service, we are still fine. We can use SDK in our function, connect to it, use it. It's just not that clean, right? Without triggers, nothing would really work. I mean, we can try to base things on timers. I don't know if I would Azure Functions for that, right? So triggers actually are the thing that makes function make sense. And triggers are more complicated than bindings. They start kind of the same because there is that attribute, there is that binding rule, but triggers have to actively deal with both of those further contexts, the definition one and invocation one. For the definition one, they have a trigger binding, which is responsible for creating the definition of the trigger for the definition of the function. What that means, they have to create a couple types, like descriptor of the invocation, value provider within an optional way to provide the value for the invocation, and that most important part, listener. So that part that is actually attaching to our service, listening for the events, causing invocations. And even on a diagram, it's no longer as clear as the bindings was, right? So once again, we are digging a little bit into the code. How that trigger binding is creating a definition. First of all, it has to define what is the type of the trigger value? And trigger value basically represents the event that is coming from the service. It has to be a very specific type, only one. It doesn't have to be the type of the parameter on the function. There are ways to convert that. One of those ways is this value provider that can be created in that bind method. That bind method is being provided that value as an object here that we have just defined, the binding context, and it can create a value provider to be used to transform that event object into something else. It not always makes sense because it's per invocation, so it's expensive. And once we take a look inside, I will tell you when it makes sense, when it doesn't make sense. The thing you always have to create is that listener, and you always have to look how that listener is treating that factory context, because that's the most important thing. It contains the executor. Executor is the API for triggering the invocation, providing the data. Last but not least, parameter descriptor. A descriptive way of telling us developers what has been invoked and why. It has to contain the trigger name, parameter name, all the other potential attributes that the author decided are important, and it needs to nicely format it in a string for us, so we can read it. You can actually meet those strings in console if you are running Azure Functions locally. They will pop up. They are there in the logs. They are for you to actually understand when which invocation has happened. So let's dig a little bit in those two last components. Value provider. As I said, it's an optional way for transferring that trigger value into something different. And it lives in the integration context, and it has the same characteristics as value binder. Because it's being creating per invocation, it actually already gets a captured value that is supposed to transform. It needs just to tell Azure Functions to what type it's transforming, so that type can actually be validated with the parameter, not the trigger value. And it can use whatever is there in the integration context to transform that value. And that's actually the only thing that makes sense to use them, if you need that integration context. If you need access to the database, queue, whatever there is, to any of those services, any of the state. So for example, you have an event, but you want to query something from the database to have some additional metadata, enhance it, then it makes sense to use it. If you don't require that integration context, don't. There are better ways, more efficient ways, which are not using resources per invocation. And you will see that in every extension, that other way that we're going to get to is a lot more often used than this one. This is only for special cases. Now, the listener, on the other hand, it has to be there, right? It has a typical API of a background service in modern .NET. If you have been working with .NET in different contexts, let's say ASP.NET Core, you have been writing hosted services, the same API, right? Or you have been generally writing background services in .NET as application using the worker template, the same API, right? That's pretty standard API for an in-memory service with a full life cycle. So when you are looking to understand what is the actual trigger characteristic of the extension you are using, because that might be important, that creates limits for you, you need to find that start method. It will contain usually 2 blocks of logic. The first block will be the state management, because we are talking Azure Functions, highly parallel environment, a little bit fragile. Things can happen. Those lifecycle methods can get called multiple times. So you will always find in all of them some state management to protect from being called multiple times, because if they wouldn't, bad things would happen. Something as mild as just wasting resources for having multiple connections, or something as serious as executing functions multiple times for the same data. So only after that state validation, there is the actual logic when you can learn what particular service is doing to get to your data for you. What, is it using some kind of SDK? Is it using pooling? If yes, what options you have to actually play with it? What limitations are hard-coded? Whenever you are in doubt, you can go there, read that, know exactly what is happening. Basically, everything can be happening here. The only limitation is it has to be asynchronous. It has to return task. That task represents the listener to the Azure Functions. Whenever Azure Functions decides to shut down a listener because, I don't know, we are scaling down to 0 or something, it will tell you to stop, cancel. So an extension will detach from the service, clean up, stop that task. To wrap up the triggers, we are missing that one arrow between the binding rule and the trigger binding. As you're already expecting, it's a factory. In case of triggers, those factories are quite simple because they have one job to do: try to create a trigger binding for a function definition. There is a context. In that context, there is a parameter. In that parameter, there is that attribute. In definition context, so that's a unique place that you will actually see the extension code calculating those values from the settings, from the expression, passing them down so they can be cached. But generally, there is not too much complexity here. Because a lot of the complexity that we could expect here is actually extracted to those additional components that fill up those rectangles. Because if all the code would have to go to this, that would be really cluttered, right? Except of integration, it would have to be doing other things. So there are other components like validators and converters to actually take some weight away from those components. They are also registered with the binding rule. Converters can be registered as either specific types or open generics. Every registrations tell Azure Functions which 2 types can be actually converted. And this is the efficient mechanism to cover that gap between the types that triggers, input, supports directly, and different parameters of the function. Because when Azure Functions is making that match check, it will look for converters. If there are converters, it will happily use them. So this is the way to extend the number of supported types. Validators, on the other hand, they are there to take away the responsibility of validating the definition of the function. There are simple methods. They are being given the instance of the attribute for that definition, type of the parameter, and any cross-validation on that definition can be done here. If there are some properties which values depend on other properties, here. If there are some properties which values depend on the type of the parameter, here. If those validations fail, Azure Functions cannot start the function definition doesn't match the bindings. So now we know there is a bunch of other stuff in that extension, right? There are bindings triggered and some supporting types for them, validators, converters, and those services I was mentioning that are doing the heavy lifting. What we don't know, if we actually want to understand a specific extension because we are using it, is how to start going through that. Right now, this is all tangling in the air, right? How to configure such an extension? There is a specific entry point for every single logical one. That's the extension config provider. It has to be decorated with the identifier of that extension, and it is the point of contact between the logical extension and Azure Functions, because this is being created from dependency injection container. So it can ask for dependencies through constructor, configuration, option, services. It can later use those dependencies in the initialize method. This is where those binding rules are being created. So all those dependencies can be captured, passed to those factories. That obviously has a consequence because everything which is captured here becomes a singleton, We don't like singletons, especially in a highly distributed environment, because that means there needs to be a lot of code dealing with parallel execution. If you are doing connection pooling, caching, that becomes problematic. And you will notice in those services that this code is usually complex to handle that. There's also one more thing that can be done here, and that's once again registering converters. And what's the additional values of registering converters here? Well, it enables a certain trick. And I'm using the word trick because it can be magic if used not properly. The technology under the trick, which is named extending other extensions, is the fact that there is one global converters manager in the entire Azure Functions app instance. What that means is that converters registered by a single extension can be seen by another one. What that means is that, let's say you have a function, and you are using a certain binding, and you have a ton of business code, and actually your business code requires completely different type than the binding supports. So you usually have some conversion code in your function. And that conversion code, if you are unlucky, can spread across your functions, right? So you will want to extract this, and you will create some static utils or something. And that's not nice, right? You can extract that code to a converter, wrap that converter in a very small extension because it doesn't have to have anything else. It can be registered globally, no binding rules. Install that extension. The extension you have been using for the input will see that. You can change the type of the parameter of the function, and it will just work. Of course, if you don't document it properly, it will be magic. Nobody who is not intimately familiar with Azure Functions will figure it out what is happening. So if you are using such a mechanisms, which are in the bigger solutions quite useful, document them so people know what is happening on. So we have that entry point to a particular extension. If you would like to start with a code base for anyone, you are missing just one more entry point, the entry point to the entire assembly. That's the WebJobs startup class. It has a single method, configure, a builder. That builder has a more or less typical dependency injection API. You are registering your extension config providers here, your configuration, your services. This is how it works. This is actually almost makes that complete. This is actually enables us to track the entire path of those extensions where Azure Functions is starting up. Let's say we have a function up. We brought some extensions, we usually do. We deployed it to Azure. Azure is starting our function up. The Azure Functions runtime will scan all those extension assembly for those WebJobs startup classes. It will call the configure method, register or extension services. It will then ask for all the extension config providers, call the initialize, create all the binding rules. It will then scan all the functions definitions, match to the binding rules, trigger bindings will be created, that will create trigger listeners. They will be listening for events. Events will come, hopefully. Invocation will happen. That will go back to to the binding rules, get value binders, asynchronous collectors. We have our entire integration stack. If we want to, we can understand how it works for a particular extension because it's no longer magic. So we are happy. We are understanding our solution. We can go to production. It will work. Or not. Various things can happen, right? We are developers, we are responsible for writing code, right? Azure is responsible for making it work. But when we are doing that, when we are deploying this stuff to production, somebody will most likely come. That somebody will be either an architect or tech lead or some more experienced person, and part of his job is to make everybody feel safe, right? Regardless if they are safe or not. The way that person is doing this is by asking questions and getting answers that make everybody feel comfortable. And those can be different questions, more or less matching the situation. I mean, you can have a standard like list of questions. Regardless of the approach, there is usually one question that always comes up, right? Whether it makes sense or not. Will it scale? And when asked this question, what will we answer? Well, it will. How? That's Azure Functions. Microsoft is telling us in the documentation that it will scale up to demand. It will be fine. It's magic. OK. So we go to the production, and it doesn't scale. Or it scales in a way that we are not expecting it to scale. Why? Because we trusted the magic, right? And that's the consequence. It would be better to actually understand what is happening. Can we understand what is happening? Well, how Azure Functions are scaling? Azure Functions have a component. It's called Scale Controller. It's not part of any of your function apps. It's there in the overall infrastructure of Azure Functions. Based on the functions definitions from your function app, it's attaching itself to all those different Azure services, monitors, queues, databases, what is supposed to be done there. Based on that information, it decides how many instances of your function app it should create. That's the unit of scale in Azure Functions. Single function app. More scale, more instances of the function app. Less scale, less instances. And that's all. That's how it works since Azure Functions version 2. And that's actually problematic, because that's still kind of magic. First of all, we don't know exactly how Scale Controller works. It has heuristics, obviously, but we don't exactly know them. So, as every magician, it can perform only the tricks that he has learned to perform. If there is anything in that function app that he doesn't know, and that is basically every custom extension. There are even 2 extensions from Microsoft that he doesn't know anything about, RabbitMQ and Kafka, because they doesn't match directly in anything in Azure, so what it can do, it will not do the trick. Also, as every magician, it will not do the trick if we break the scene that it has prepared for the trick. And how we can break the scene? We can make a proper infrastructure around this. If you wrap Azure Functions in virtual network, as you generally should in most instances, you put up firewalls on those services, use private links, private endpoints, Scale Controller goes blind. It can no longer do anything. It will not scale anything for you. And that's a serious problem, and Microsoft acknowledged that problem. Microsoft is even trying to give us 2 solutions to that problem. We already have one. The one which is coming with the Flex Consumption Plan. It will be exclusive to Flex Consumption Plan. In Flex Consumption Plan, when Azure Functions app is being deployed to virtual network, Azure Functions will deploy an additional component. Trigger Monitor, it's named, just not to confuse anyone with anything else. And that component will be responsible for reaching to those services, feeding the data to Scale Controller. Scale Controller will be able to scale our function app. What we already have is that something that Microsoft enabled in 2019, they figured out in 2019 that there are, in fact, those extensions, and they are already doing a lot of integration stuff. They are always connected to those services. So maybe they can participate in gathering metrics, voting how to scale. And later in 2023, so last year, Microsoft also decided maybe they can tell how many workers they would want. After all, they know what they are doing, probably. So now there is an option for those extensions to feed the data to Scale Controller, metrics, votes to scale, how many workers they want, and they can be responsible for monitoring those services. I'm saying possibility and can because that's not the default option. It's not there for the consumption plan. Well, in consumption plan, things can scale down to 0, so there will be nothing to host that code. It's only for the premium plan. Additionally, Microsoft motivates that this is a solution for scaling in virtual networks. And until Flex Consumption, only premium supports virtual networks. So this is why it's there. And it's not there by default as well. You have to turn it on. And when you turn it on, you get that unique possibility of actually understanding how your function is scaling down to every single heuristic. Because back, it's in the code that we have access to. It's on GitHub, right? And we can find that code in the extension and read it. It's attached to listener, so we already know where that is. If a particular extension is participating in that scaling mechanism, the listener will have methods to return 2 additional components, Scale Monitor and Target Scaler. Scale Monitor is that older component. It's responsible primarily for gathering metrics. How does it gather metrics? That depends on the service, obviously. I will use Cosmos DB as an example, because we seem to like it on this conference. So in case of Cosmos DB, the trigger is based on change feed processor. And change feed processor has a change feed estimator. So this code is actually creating an instance, asking for the information. The information contains how many items are there waiting to be processed, and how many list documents are there in the list container. And list container is something that is managing state for the change feed processor of Cosmos DB, right? Very internal knowledge to Cosmos DB. That's the advantage, because the people who are writing the Cosmos DB extension, they knew Cosmos DB. Surprising stuff. And this will be needed because once in a while, when a scale iteration comes, the scale monitor is being asked to vote. He's being fed back all the metric it has gathered, provided to scale controller, and it's supposed to cast a vote. And the vote can be scale out, scale in, neutral. And what Cosmos DB extension does based on those metrics? Well, it looks at the sample. If the sample is small, it will say neutral. I don't know enough, I don't want to do any harm. If the sample is big enough, and the number of remaining items is growing or is very high, scale out. Unless the number of existing workers is already equal to number of the leased documents. And we are going into internal knowledge of Cosmos DB again. The way change feed processor works is it's very nicely prepared for parallel processing, but the upper bound limit is that every parallel client needs to own at least one lease document. So if we have more clients than lease documents, we are basically wasting resources. They will not process anything. So the Azure Functions extension knows that. It will not scale beyond that. What's more, if Azure Functions extension for Cosmos DB will notice that that container has been restructured, once again, internal Cosmos DB knowledge, it will vote to scale in regardless how many items there is remaining. And it obviously will vote to scale in if the number of items is falling or is very low. If things are steady, it will vote neutral. That's more or less the heuristic for Cosmos DB, but what is important, we can go to GitHub, find the extension, understand that heuristic in details. That other component, the target scaler, is actually that newer one. It's responsible for providing an exact number of workers that the extension would like to have. And there are different heuristics for that. Cosmos DB has actually a very simple one. It's saying that at minimum, I want one worker per 1,000 of items remaining. That's my minimum. That's what I want, right? There is also a certain Azure Functions functionality that is being often implemented here. It's named dynamic concurrency. And if you read documentation, it tells that this is a way to limit how many items is being processed in parallel by a single instance. When it's implemented here, this is actually what a lot of extensions are doing, it's being implemented as a simple division. So let's say dynamic concurrency is 100, there is 1,000 item remaining, let's divide 1,000 by 100, that gives us 10. If we get 10 workers, we are happy because theoretically, every worker will process 100 items. Will it? Will even that extension get 10 workers? Not necessarily, right? Because there are other conditions, and the step in a scaling iteration is +4, -4, so it certainly will not get there immediately. But what is the biggest value for us as developers is that this runtime scaling capability is sitting in the extensions. If we are using it, we can analyze it, very carefully understand how our Azure functions should be scaling on a level of a single trigger, single extension, and the level of the entire function app. Because as you could notice, that scaling mechanism is attached to a listener, right? And how many listener is there in every function app? As many as triggers, right? So let's say we have a function app which has a Cosmos DB trigger in it and a service bus trigger. And there's a lot happening on the Cosmos, very little on service bus. The Cosmos trigger will vote scale out, scale out. Service bus, scale in. What if we have a lot of triggers? Where if there is a lot of entities allowed to vote, and they have different needs, bad things can happen, right? So if you are seeing that your function app is scaling in some erratic way, not what you would think makes sense, it might be time to actually analyze characteristic of every single trigger, what's the data input, and maybe change the granularity of your function app. This is when those low-level details that we are usually not exposed to impacting the architecture of our solution. In fact, the Flex consumption plan intends to fix some of that, only exclusive for it, not for others' plans. It's bringing per function scaling, not for all the triggers. For example, not for HTTP, I believe not for durable function, and something else, I think. But for others, it says it will orchestrate that. It will actually put that function up on different instances and scale those instances depending on the trigger it has chosen for those instances. So it's going to try to handle that, right? There are some caveats to that, but it's better than nothing. And from like big picture perspective, this is all. We have went through that entire integration responsibility and its consequences to our design. Well, there's one small elephant left in the room, the isolated worker model. The isolated worker model is something that has been there for all the languages except .NET since Azure Functions version 2. For .NET, we have it from like 2020, something like this, something around .NET 5, .NET 6, right? And soon we will have only it for .NET. Microsoft already announced November 2026, end of support for Azure Functions .NET in-process model. Done. That means that in 2026, all the languages will have the same situation. We have two processes. One for the function host, the other for the isolated worker, which is running our business code. And those processes are communicating. In case of .NET, that's gRPC, which is nice, more performant. Other languages usually have to stack with HTTP. And all we have discussed so far, all that integration capability, it sits in the function host. In that case, what sits in that isolated worker? Well, depending on language, there are different mechanisms to actually represent those bindings. In case of .NET, that's new extensions, let's say. But they are all just bridges to those in the function host. How they are making that connection? Well, that depends on the language, right? In the case of .NET, that's actually very developer-friendly. There is a direct information in that assembly to which in-process extension it is mapping with an exact version. And the tooling will handle all of that for .NET developers. Lucky them, right? In case of other languages, that's host.json responsibility. There is a simplified way of registering extensions from Microsoft. There's like a single line that you can put to get the Microsoft bundle. But if you have something custom, you have to manually play with host.json so it is able to drag it from somewhere. On top of that, there needs to be a mechanic to get in those definitions, right? We have on our functions. In case of .NET, new attributes. In case of other languages, those annotations in Java, those definitions in functions.json. In the end, they all get serialized, so they just represent some DTOs, send over that connection, and the functions host will recreate the attributes for the in-process extensions, find the proper binding rule, the integration will start happening in the function host. The input payloads for inputs, for triggers, output payloads for outputs, they will all be handled there. And they will be sent across that communication channel, right? And that's a limitation. Because there are certain bindings, there's a lot of them in .NET, but there are also in other languages that support very specific types, SDK types. Like, I don't know, client to a database, client to a queue. You can't send that over gRPC. That doesn't work like that, right? So what actually Microsoft had to do to enable that, and this is why we still don't have a parity in .NET between the in-process and isolated worker, is that there is some kind of mechanism, different for every language, to run some of the integration code in that isolated worker model extension. In the case of .NET, once again, converters, right? In other languages, different mechanics. They can usually be in every language attached to inputs or triggers, and they can take over the process of that sending over the wire to get the value, right? They can use whatever they have accessible given in given language. In .NET, in fact, those assemblies can register their own dependencies, services, etc. Based on that, they can create the value for a function locally. They shouldn't have like long-living connections, etc., but they can connect something like a database client or something else, inject that directly to the function. So that enables for isolated worker model the SDK types, and also that architecture of isolated worker model is the source of all the limitations that we had things in in-process model that actually not always can be done in the isolated worker model. And that, in fact, covers the entire subjects of trigger and bindings on, let's say, after all the code I showed, I don't want to say it, but high level. Okay? There's more details, and somehow you are interested in that. The first link, it contains a series of articles that are going into details of those different things. The second link is my small polar bear. It's that RefingDB extension. It's actually simple enough that if you want to go through code of it, it will show you more the concepts than the actual RefingDB-related stuff. So it's nice if somebody wants to talk about it in context of a code. I think I'm right on time, so in that case, thank you. Thank you for your time. I hope you will find this knowledge useful. I strongly encourage you to look one level deeper to understand what is happening under the hood. And who knows, maybe you will have to write your own extension. If you have any questions, I want to make a room for the next speaker, so feel free to approach me or grab me on social media. I'm always happy to chat.
Thank you, Thomas. We'll continue with the next presentation in 10-ish minutes. So.
50 minutes, 75 slides. And I personally have had the last 30 years of a co-hosting of a common podcast with this person, or at least it feels of 30 years.
And I still love you.
Because we are so close. The love is mutual, I've been told by him. Let's welcome this person to tell us about AI things, I'm guessing. Let's hear it for Jouni Häggniemi!
Thanks. Took like 45 seconds to get him off my stage. That's awesome.
I have one more thing. Okay.
Oh, God damn it. So, how many of you are developers? How many of you are working actively with AI projects? Like maybe 20% max. How many of you are actively using Azure AI Studio? A few. Cool. That is maybe even more than I expected, because this is sort of a, I'm not going to say hidden gem, but it's a hidden piece of Azure AI. They're pushing it in the marketing. My experience is that most people don't really understand why it is there and what can I use it for. So I'm kind of going to spend the next 50 minutes covering some parts of Azure AI Studio and explaining why you might want to use it, why it might become more relevant in the future. This session is going to be way more about ideas than actually hands-on doing something. Demoing AI things is always complicated because it's stochastic, it works differently every time, but it's also very slow. So you're going to see these things through a set of screenshots and some explanations on how I feel this is going to affect our architectural decisions over time. First, one positioning slide from Microsoft, then I'm going to leave theirs. So what Microsoft is telling us is that Azure AI is this top brand that contains Azure AI services, containing things like OpenAI service as well, but also machine learning, computer vision models like Florence, speech-to-text, universal translator, so on, document intelligence, there's a lot to go on from there. Azure machine learning, the classic ML service, and responsible AI tooling, content safety, and so on. AI Studio is intended to be the user interface to all these. So the original title for this session was this: what are they trying to do with it? And that's kind of what we're going to dig into here. So I would split Azure AI Studio's functionality into 7 different buckets. I'm going to cover some of them in more detail, some of them in less. But if you look at this, it's less about new features. It's not that model that is so different from GPT-4. It's the ability to engage with any model. It's not so much some new cool feature about universal translation or computer vision. It's more about the tooling, the way you work with those AI innovations. Let's kick this off. What is Azure AI Studio? And what the hell is Azure AI Studio Hub? Some parts of Microsoft documentation say it's an Azure AI Studio Hub. Some just say it's Azure AI Hub. Anyway, the idea, it is a free top-level Azure resource that groups your AI assets. You don't have to use it at this time. You can pick any Azure resource type. You can pick machine learning. You can pick OpenAI service, computer vision, whatever. And you can just make those resources run. AI Studio is one more way to group your projects and resources. If you start building an Azure AI Hub or creating a new one, there are a few things you may want to pay attention to. First of all, there's a Heja Sverige story here. So you essentially have to pick Sweden Central if you want to do anything meaningful at this time. I hope it's not going to be like that forever, although Sweden Central is a great data center. Oh, sorry about that. All right. The other thing you should notice here, there's this thing called Default Project Resource Group. And I'm going to talk about this a bit more in the future. But you will see that this Azure AI Hub concept, it does almost nothing by itself. It's just a user interface. What it is, it's a platform for launching other Azure resources, creating AI projects and then resources for them. And that resource group, this default project resource group, that is the place that the new projects are going to be deployed into. But it's also grouping some resources by itself. So, as you can see, when you go to the next page, you will see that you're going to attach a storage account, a Key Vault, application insights, container registry. You're starting to get the hang of it. This is a free resource that connects a set of resources you need for your AI studio experiences. So essentially building those applications, and in some cases also hosting the apps. I'm going to explain this a bit more detail. So that Azure AI Studio part you see so much talked about is just a user interface to this hub. What it looks like at a resource level, your per hub resources are like this. So you have that actual hub. Then you have storage accounts, key vaults, application instance, and so on. All of this is free until you use it, because all of those are pay-as-you-go resources. Then when you start creating projects, I'll shortly explain what they are, you will also come up with other resources. So you can, for example, have machine learning endpoints, or you can have serverless deployments of some models, or whatever. There are a lot of containers. There are a lot of different kinds of resources that the AI Studio can provision for you. At the portal level, it looks exactly as boring as any modern Azure resource. There's really something else here. That button says Launch Azure AI Studio, and that's where we're going next. So Microsoft hasn't done a great job in distincting between services and projects. Their terminology is still wavering a bit here, but I think the final version, the final one published in build of Azure AI Studio kind of makes this clear. So there's the distinction between Azure AI Services. You can see it over there on the left hand side, Azure AI Services. That means all the Azure's as a service AI features. You go there. You see, it's pretty much like what you had before with all those Azure different kinds of services. You had Vision Studio, you had Speech Studio, and so on. All of that has now been grouped into Azure AI Studio. So one part of Azure AI Studio is that it's a unified user interface for all this. And you can go as deep as you want. If you pick up something like Vision plus Document, then you can pick up those Azure Document Intelligence usage scenarios from the left-hand pane. For example, marriage certificate. Okay, cool. It's fun that we have something for that. Anyway, this is kind of the services you've used to waiting for. So Azure AI Studio is, first of all, it's the unified admin panel for all those services. But second of all, and what we're going to focus on for the rest of the presentation, it's a DevOps environment for Gen AI projects. I don't think, Microsoft's opinion may differ, but I don't think these two realities are too well connected yet. They are connected in a sense, but I feel that when Microsoft launched Azure AI Studio, they wanted to do this part one. They wanted to have this unified admin panel, but their real focus is on building something new for the Gen AI projects. What are Gen AI projects? If you build a new Azure AI Studio or Azure AI Studio Hub or whatever, and you pick up the studio, you will find this kind of interface. Projects, new project. Okay, what is a project? Essentially what they are a collection of AI resources for a single purpose. The idea here is that the AI Studio gives you the tooling to develop and then eventually also deploy those resources into production use. Azure AI Studio story is also about collaboration. So the idea is that if you have a group of people working on an AI solution, they can come together and use Azure AI Studio as the tool to change how the LLM parts or the AI parts in that application work. Some of you are smelling portal-based editing in production here, and I see where that's coming from. There are some issues here. Also, projects. The hub also acts as a grouping in the sense that projects can share some resources within the same hub. So for example, you can have deployments of custom models, or you can have a compute capacity for some certain model or whatever scenario, and you can have connections to external services, indexes, databases, OpenAI service instances outside the hub. So essentially, what's happening here is just a topology of concepts. And if you create a project, it's very simple. There are no magic properties here. You're just giving essentially a name. Then you get a project view. And if you look at the left-hand pane again, there are lots of features there, and we're going to look into them. But really, it's nothing more than a container. Essentially, an Azure AI Hub is a control surface for a group of projects. We do not know what a project means. You can think of it as an application. I think that kind of makes sense. So if you are building an AI-enabled application, you might use Azure AI projects as a way to group together all the AI assets for a single application. That would make sense. From a practical standpoint, it might also make sense to have functionality for a single module of a larger application grouped as a single project. I don't think there is the right answer here. It's just like solutions and projects in Visual Studio. You can use them however you want. But you can have those shared resources and you can have those project level resources. And that's kind of the approach Microsoft is taking here. Now, the question I think some of you may be thinking about, what do we need this for? Because that is what I've been thinking about. I have 4 thoughts on the matter. First of all, as a developer, just writing code, just building the application, I don't think I need this level of control because I'm used to infrastructure as control, as code. So I can use Bicep or I can use whatever, Terraform, to provision my resources. Okay, well, the second problem or thought is, am I right? Because if I want to share resources between applications, that is always a bit complicated with IAC. Technically, you can do it. Admin-wise, you end up with different concerns. So it might be easier if you had a higher level abstraction on sharing those AI resources. But why do you want to share something that is essentially pay-as-you-go? Well, another question there is it always going to be pay-as-you-go in the future? Because many of you, if you have built AI applications using OpenAI service, you have already maybe encountered the truth that OpenAI service does not always perform as you would expect. You are seeing bottlenecks in performance. You are seeing you're hitting the tokens per minute gap. So maybe you want more capacity. Well, the way you use that capacity is you buy provisioned capacity, or PTUs, provision throughput units is the term right now. That is kind of the enterprise approach to using OpenAI service. If you want to go PTUs, then maybe you actually want to share one because you don't want to have a PTU per application. That's just going to be too expensive. So we've been used to having these AI services available in a pay-as-you-go fashion, but as you go to custom fine-tuned models and so on, where you actually have to pay for the capacity yourself, then you want to pool the resources. So that is something to think about. Third, Microsoft sees a particular need for LLM apps. Control, meaning security, governance, monitoring, content safety. I'm going to openly say that I don't see all that much of this need. But that is also because the apps we're building are small. They're simple, and that's also point 4. Because our apps are so simple, we don't need all this control. But if you think of it, Microsoft's approach to this, they are like 5 years ahead of us in terms of scaling AI apps and thinking about responsible AI. What they are encountering now is probably something we're going to encounter in a few years. So I think this may make sense from a governance perspective in the future. I'm not seeing the benefit right now. That said, this part was about governance. This part was about organization. Then we're going to go into what can we do in terms of technical features. Alternate models and hosting. How many of you have actually used a model other than GPTs? Okay, a few. How many of you have used another model in production? Nobody. Yep, that's how it is. Our AI fever is open AI fever right now. It doesn't have to be that in the future. And not only that, but it can also be a multimodal future. So we think that GPT-4 is the awesomest whatever thing ever, because we've had so much experience with it, and GPT-4o is amazing, and it feels like Sam Altman is always pushing the frontier, and we're getting the best things from them, and that has kind of been true. The problems come when you start scaling things, because you may encounter the fact that actually it is pretty expensive to use GPT-4 for everything, even though you may need more performance, you may need more scalability than you can get with GPT-4. You may need to run locally, which is something that Microsoft is now doing with the Windows Copilot Plus strategy, so that's one thing. Or you may need to fine-tune something to a special need, so you may know that your domain needs a fine-tuned model. It's going to be rare, but it can happen. So these are scenarios where you can't just pick up the whatever Azure OpenAI service is now offering, GPT-7X or whatever is the newest and greatest thing. We are going to want to think about which model to use for which task. And if you think about a product like Copilot for Microsoft 365, the product team has to think a lot about which model to use for which scenario, because they know that GPT 3.5 is going to be able to perform certain tasks just as well as 4.0. But 3.5 is going to be faster, it's going to be cheaper. And yeah, maybe 4.0, maybe 4P or 4N or whatever, it's going to catch up. But then we're going to have GPT-5, and everybody's going to expect everything to run on 5. But 5 is, again, going to be expensive and slow. So we are going to be thinking about this, the more data we are going to pass to the LLMs. So we have these tools. Let's kick it off with the model catalog, because this is something that Microsoft is demoing every now and then. If you have good eyes, you can see that there are currently 1,672 models available in the catalog. And essentially what Azure AI Studio brings to you is it enables you to just spin up any of these models and have an endpoint you can call. How's that going to happen? Pick up a model from this list. You will see that this is Phi3, small, 8K instruct. Those names are horrible, but what it means is we have 8,000 tokens. And if you read the text, you will notice that we have 7 billion parameters. And now you can feel very wise when you know that. I have no idea what it actually means in practice, but that's what happens. What is good about this is that there is this box that says intended uses, primary use cases and use case considerations. These kind of give you an idea on what kind of material the model has been trained and tested on. So you should have a rough understanding of, is it reasonable to try to use Phi3 for my Finnish translation or Savo poem application or whatever. You can also test them. You can see there's a box where you can just type anything and the model will respond to you. So Microsoft is hosting copies of at least some of these models so that you can test them. Now, when you go to deployment, what actually happens is that you will just create a deployment. Okay, that's not very well visible on this screen. So there you can see you can pick a VM size, and for this Phi3 model, the smallest size you can pick is a VM that costs about $5 an hour. So that is not super cheap, and now we come back to pooling resources. So this is something you need to consider. Some of those models require significant investment to run. Also, one thing you need to notice, if you want to go to production fast, you will need to apply to have production quota. So Microsoft support will give you a production quota when you ask for it, but out of the box you will only be able to provision endpoints for a week for some models. These are things you need to consider, but you will want to test first, not go to production directly. Once you're done, you will get a host name, and then Azure ML will host the endpoint for you. So you will just find standard instructions for that in Microsoft Learn, so no any special things up there. About these endpoints, you can see when we provision one, it just has URLs, it has primary keys and so on. So this is a very standard Azure resource. You really want to start with playing this on the playground. So if you have used Azure OpenAI Studio, you know there's an Azure OpenAI Studio playground. There's also an Azure AI Studio playground without the open part, but it's still open. So if you use this playground, you can chat with the model, just as you did in the previous screen, but now it is your own model. And as you can see, on the right-hand side, there is a deployment choice. In Azure OpenAI Studio, you classically had that deployment drop-down, only contained those OpenAI models you had deployed. With Azure AI Studio, there can be any model in it. Now, if you try something like, let's say, summarize the following text without marketing hype, and then I paste it in a piece of documentation on Azure AI Studio from Microsoft Learn, then you get some kind of summary. And in this scenario, I found out that actually Phi3 summarizes quite nicely. So this fast, like 2-minute test, has proven to me that I can actually use Phi3 for my scenario if I want. Is it going to be cheaper at $5 an hour? Maybe, if I use enough of it. So these are kind of the things I'm going to have to think about. Also, what I'm going to have to think about is that these small models, they often have their issues. And we're going to come down to AI testing and these things a bit later on in the presentation. When I tried to do the previous test, this one, I actually failed because I didn't remember that I can't have a line feed in the input box. So I only submitted this. Summarize the following text, remove all marketing hype. What was the response I got? The text provides information on product design to improve sleep quality. Where did that come from? Then it goes on to describe lines and lines of some kind of a mask that goes on your face. And it helps me achieve deeper sleep by providing a cool and dark environment. So that's a hallucination happening right over there in a very simple prompt. I don't get this on GPT-4o. I don't get this on many of the bigger models. So you have to test if you want to use different models.
But it's correct that the battery life is not specified in the text.
Yes, it is absolutely correct that the battery life is not specified in the text. Thank you, Saka, for your contribution.
I'm here.
We are so happy about that. Okay, so there's absolutely no substitute for testing yourself, but if you want to look at what kind of models are available, there's also this very cool and actually very useful feature called model benchmarks, where you can go and see different kinds of models arranged according to test results on categories you choose. So you can see like maybe the top 3 models, the top 5 models you want to go deeper into testing yourself, because you can't test 1,600 models. Now the question probably many of you thought about was, do I really have to pay $5 an hour for virtual machines? That seems so last year. You don't, for some parts. So you can also filter the model catalog by choosing serverless API. You will see that if you choose serverless API, you will only have 30 models. But for those models, you will be able to go much faster and much easier. So for example, I'm going to pick up here Llama 3, the 70 billion parameter version. And now on the deploy page, I don't have to choose a VM, but I'm just going to see that the inference is going to cost me like $1 per 1,000 tokens and so on. Very much more like Azure OpenAI service. Now when I deploy model, I just get an endpoint into the public version of Llama 3. I can't customize it, obviously. It's just the way it is with Azure OpenAI service. But this is the way to get some services available for you cheaper without a fixed cost investment. And now I can try something like, let me talk Finnish to that one. So osaatko puhua suomea, and it will give me a reasonable answer. So with Llama 3, I can use Finnish. I can't always do that with Phi 3. It depends. Now I can also connect other resources. For example, if I connect GPT-4, I can have that as well. One thing to realize here is that if you look at this chat session, I still have Llama 3 selected. I only have an input box. Start typing here, nothing else. If I pick up GPT-4, then this is going to look like Azure OpenAI service in the sense that I have these all features familiar from there. So I can adjust the model parameters, temperature and so on. I can also use this add your data, and I can also enter a system message. So this playground experience differs per model, although from a practical perspective, I think it's only that if you're using OpenAI models, it's going to have more features than with other models. But in this sense, it is important to realize that Azure OpenAI service, to my best understanding, no longer has any unique features. You don't have to use Azure OpenAI service and its playground and its Azure OpenAI Studio, because everything is here in Azure AI Studio. Whether you like it more or not, that's a matter of preference, obviously. All right. So essentially what we have is multiple models under a single surface. We can host those 1,600 models in VMs, but as serverless, only 30. You can have these projects, these models deployed at an AI project or at the hub level, depending on how you want to share them, what's your way of arranging resources. These same control surfaces, in every sense, you have. I'm going to be talking about prompts, evaluations, and so on. All of this is going to be available regardless of where this model came from. And that enables you to do some scenarios like test your application on multiple models easily with some constraints. Let's talk about prompt engineering. And this is maybe the part where there is most value in the future. But there are also quite a lot of caveats, and I am not sure how to integrate this into my personal workflow, and you will soon see why is that.
Question.
Yeah.
On the pricing, did you mention the price of the PTU?
No, I did not mention the price of the PTU.
Isn't it the case that the €5 per hour is quite a lot cheaper than the PTU?
€5 an hour is cheap compared to some of the PTUs. I think the PTU pricing is currently, you can only get it from a Microsoft salesperson.
Yep.
I hope that will change in the near future. There are no public pricing lists for PTUs. I'm sorry about that. If you're an enterprise customer, you will know. They have tried to sell it to you. All right. So prompt engineering. All of us do it at some level. How professionally we do it differs based on what we're actually trying to do here. But there are a lot of questions that Azure AI Studio can sort of help us resolve. First question, what is a good prompt? There is no universal definition. Usually, we think it's a good prompt when we get good results. The problem is that when you do 100 or 1,000 or 10,000 executions, you will get some part of the results that are good. Then there are going to be a few really bad apples. So The question is, how do you know it's a good prompt? How do you evaluate and classify prompts as good or bad? Then, more and more applications in the AI space are actually being constructed out of several prompts with logic between them. How do you test that? How do you manage it? How do you write such a code? How do you share that code to others? The simple answer is, well, I use C# and then I call the OpenAI SDK, and that works as well. If you want to go to a higher abstraction level, then this is something that AI Studio may be able to help you with. And then, referring to our last section, which models can I actually use on this prompt? Which models are able to reliably answer this question? And that's where we're going to head next. Let's start with the prompt catalog. And this is not as interesting as it sounds like, but it makes kind of sense. So Azure AI Studio has this thing called prompt catalog. It's like model catalog, but this is for prompts. If you go to the internet, you can find like 700 prompting guidelines in the first page of the Google alone. So you don't really need prompts. What you really need is an experience you can easily test different things on. So you can see there are kinds of different kind of scenarios: advertising summary, personalized marketing, parse unstructured data, whatever. My eye focuses on natural language to SQL. That is an interesting example. Let's look at this prompt. What happens here is that the system message is set up with a few PostgreSQL tables described in a certain syntax. And then there's a definition that we want Accurate to list the names of the departments which employed more than 10 employees in the last 3 months. And then select. Now the question is, if we want to have a scenario like this, which models can actually complete this? Well, let me try it, because you can always do open in Playground. That is what Azure AI Studio is for. These things are simple to try here. So if I open it in Playground and I do GPT-4, no surprise, GPT-4 does it pretty nicely. It returns only the SQL statement completion you want, and this is actually a fairly good implementation. Depending on the SQL variant, that might actually even execute. You may want to instruct it if you want a specific dialect of SQL. Let's try it in Phi 3, a very small model. It also does a fairly good job. It uses a different dialect, so that would not execute on SQL Server maybe, but you still get a reasonable result. You also get a lot of text describing what you're actually doing, so that may be a plus or minus depending on what you're doing. And you can also try this on Llama, and you will get a response. But now, if you spend some time reading that, you would realize that the answer is wrong. It is a fairly subtly wrong one, because the other models actually completed the condition right. They do return departments with more than 10 employees in the last 3 months. Llama returns departments that had paid at least 30 salary payments, not different persons. So these are very subtle differences, but this kind of shows you how complicated it is to actually test models, because the differences can be so small and still so critical. But if you want to go down this route, then Azure AI Studio may well be your tool. And the next things that are going to help you with that is our prompt flow and tracing. And I'm going to talk about these together because it's different to tell them apart at some point. How many of you are actually using prompt flow? One. Cool. Prompt flow is an open source project built mostly by Microsoft, but contributed by others as well. It is a Python-based toolkit for creating executable flows that link LLM's prompts, Python code, and other tools together. That sounds complicated. It also sounds a bit like LangChain or semantic kernel, but it's not. What prompt flow is, it's a toolkit for creating deterministic flows. Essentially, it is a beautified version of creating YAML files. Again, I think half of the world is that right now. So essentially, the whole toolkit creates flow.dag.yaml files that describe a flow. They are available as command line Python tools. There is a VS Code extension, so you can use a graphical designer to build those flows, and you can do it within Azure AI Studio. And I would say that unless you're really hardcore, you will want to use the Azure AI Studio one. When you realize the benefits, then you're going to go with the Visual Studio Code. What does a flow look like? Here's an example. Chat with Wikipedia. So this is a very simple RAG scenario, so retrieval augmented generation. We pick up some information We send it to the model, and then the model will use it to answer the user's question. Here we have an input, which is a user's question. Then these are the steps built into the process in this particular flow. First one, extract query from question. For example, if I ask like, what's the capital of Finland? Then it's going to understand that that user is looking for something called capital of Finland. That is what a large language model does well. It understands the user's intent and picks up the key phrase. Then we have get wiki URL, which what it essentially means is it formats out a Wikipedia search URL that contains the search keyword found out by the LLM. Search result from URL, this one, picks up the Wikipedia pages related to this search, and then process search result composes a unified search result for that. Then we have this part called augmented chat, which is the typical RAG prompt, so it picks up the Wikipedia source information and the source links, and then asks the model to answer the user's question. What this kind of thing looks like is that typically you have a prompt here, extract query from question, and you have a rather complicated prompt because it contains some kind of guidance to the model. How are you going to pick up the search terms? So that first stage is a call to the LLM. It's not shown in this picture, but here connection, you can specify which model this is going to connect to. And here you can also see it's an opportunity to do a multi-model flow. You could, for example, have this first step run on a different model than the last step, if that made sense to you. The second step, get wiki URL. Well, that's going to be Python code, because as I said, prompt flow is a Python toolkit. So now you have a piece of Python code that actually constructs you those Wikipedia search URLs. And so on. I'm not going to show you all the stages because there's no sense. If you have built RAG applications, you roughly understand what's happening here. If you have not built RAG applications, it's just a flow that gathers the user information, gathers the background information, and then uses an LLM to construct the answer for the user. What it actually looks like in practice is when you execute it, it looks like a chat. And the thing about prompt flow within Azure AI Studio is that you can easily test these things. So there's a tool called Start Compute Session. What it essentially does, it spins up a VM. By default, that VM shuts down after 1 hour not using it. So it spins up a VM that can run your flow, and then it executes it. It opens up a chat window, a playground for you. You type in a question, what is the capital of Finland? And then it executes all these steps, as you can see here in the middle of the screen. And once they're all completed, you have a debugger-like experience looking at it, execute them. Once it's done, it's going to give you an answer. And that's going to be a fairly good one at this, because the question was a good one. It was easy to find from Wikipedia. If it had not been, or you wanted to debug something that went going on there, there's this thing called view trace, which is another good reason to use AI Studio and prompt flow, because finding out what happened when you're doing something by hand can always be something, can sometimes be quite complicated. What happens when you use view trace is that it opens up a tracing view where you can view the whole execution tree here on the left-hand side. You see which steps took how much time. And if you go into any of the steps, you can see the input and output results. So that kind of helps you understand which stage should I tune to get this better. So this is kind of the first part where you can actually say Azure AI Studio provided some value. This is fairly hard to do by hand. Is it easy to do using prompt flow? Depends on if you know how to write Python. So that's kind of one of the problems with this tool. But it's useful, and the samples available out there in the prompt catalog, they actually help you get started even if you don't know Python. So that helps. Another thing, I don't know how many of you have actually tried prompt variants in the sense that you have had one prompt and then you had looked for a better version of it. Anyone? Yeah, maybe one or two. Yeah, this is something that comes up if you're trying to tune an AI application to consistently return the right answers. It's very hard to know what's the best wording for prompt. And there is, I don't think there is any magic source available for this one. You have seen many guidelines on the internet, but realistically, I think it's mostly about trying things. LLMs can help you in the process because they can create the variants themselves. And that is something that has been integrated into the prompt flow. So take this another flow that is very simple. It does a summarization of users' meeting notes. So I have configured an input that only contains a single text block of meeting notes. Then I have this LLM prompt. You are a bot that generates a succinct summary of a meeting's notes. Use whichever language the user is using in the notes. Be brief up to a length of 200 characters. Focus on facts and end results and remove personal opinions. That is my prompt. Now, I don't know if this is the best way to word that request to the model. There is no way to know. I can only test it. And as I've already shown you, prompt flow is an easy way to test things. But if you want to test different variants, the easiest way to approach that is to use this button called Generate Variants. Then I'm going to tell it, give me 3 ones. Give me 3 new wordings of this prompt that do roughly the same thing. Then I'm going to choose which model is it going to use to generate these variants. I generally think GPT-4 is the best one for this, but you could probably go somewhere else as well. Okay, this one was my original. Then it starts generating. I'm only going to show you 2 ones, but it generates versions. If you spend even 10 seconds looking at those, you will realize that they are roughly the same in intent. It's only minor details, stylistic details, but the LLMs respond to those, and sometimes some of those variants perform better than others. If you test with a single set of data, you may not even notice the difference. If you test with 1,000 inputs or 10,000 inputs and run those tests like 5,000 times or 10,000 times, you will usually know this difference. And this is kind of the direction where we're heading in. If we are trying to build, for example, like a B2C chat, where we actually have to be very aware of each response going out because everyone can be a PR disaster, then we're going to need all this testing. Anyway, I have these competing prompts, variants. Then I'm going to enter some meeting notes about Iglooconf planning. And I'm going to have this model condense this stuff together. This is the reason why Saki came to the presentation. Awesome. What a waste of his time. But I wanted to waste it, to be honest. Okay, so I can run this summarization.
Who didn't send an abstract to this speech?
Yes.
Until last week. I do agree.
All right. That's enough love for this presentation. So as you can now see, the summarization box has an echo, sort of. There are multiple summarizations going on because prompt flow is executing this flow in several different copies. Now I only had variants for one of those prompts. I could also have variants for several ones of them, and I would have to look at all the combinations. But this flow is so simple that I only need that one. Okay, well, then I'm going to get different summaries. And all of these are essentially the same. There are no big differences. Some of them adhere to the length requirement better than others, but these differences are, as I said, not too different because I only tested with one piece of data. But the value proposition here is that you can actually do this testing with one piece of data, 100 pieces of data, 1,000 pieces, and then you can evaluate the answers together. Okay. So this is valuable, but now the question is what is the role of prompt flow when we go into production, because this was sort of a dev time experience. You can do many things with it. You can use it just as an IDE, or you can deploy these flows. So if you do a deploy flow, what actually happens is that Azure ML, or Azure AI, or whatever you want to call it, it will deploy a virtual machine, once again, a virtual machine that will host your flow. It will give it an Azure ML endpoint, and then you can just use it to a REST API to call your flow and get the results back. And this is sort of valuable if you want to do it that way, because what prompt tooling actually does here is you can get a sort of an experience from idea, prompt, Python code, all the way to iterating it, finding the good prompt, then trying variations to find the best prompt, then doing tracing to actually understand what's taking so long and where it's going wrong, then doing the deployment, and then having monitoring. So if you do this deployment, you will also be able to monitor your production executions as well. The question is, do you want to use this? Because what it means is that you will have Python code and prompts separated out of your application code into this thing called Azure AI Studio. I don't know the answer. We still have way too little experience in LLM architectures to tell the final answer. I think this is one possible architecture. But it has its flaws. One of them is Python. Nothing wrong with Python. It's one fixed technology you need to stick to if you want to use prompt flow. Another thing is, do you even want deterministic flows? Because we are all the time moving towards Copilot-style solutions where users are not just asking for a piece of information in the chat. They are asking for action. They are asking for something like create me a travel invoice for my last week's trip to Stockholm. And you expect the Copilot to be able to parse your intent and then trigger processes. And that is not a deterministic flow. It does not flow from up to down. No. It flows to a decision point where the model or the planner actually decides what's going to happen next. We are going to call this travel invoice plugin or whatever. The problem here is that prompt flow is not really engineered for this kind of activity. It is engineered for deterministic flows right now. The other question is, do you actually want this control inside your application? Because you can use something like semantic kernel, which is available for Python, Java, .NET, and run this kind of decision-making and flow control and planning sequences right inside your app and control it within your code. That's good in the sense that you will have all the control available locally. That's bad in the sense that if you want to update the LLM logic, you will have to update your application. So what this hosted prompt flow actually enables you to separate out your AI parts from your application code to this Azure service. It's a higher abstraction level service. You will have the AI, the intelligent parts of your app running on Azure, and you can always go and edit them just using prompt flow in production. Now that sucks. So essentially what this means, you will end up having some kind of LLM ops. So you will have GitHub or Azure DevOps with deployment pipelines pushing into prompt flow. All of this is possible, but it is very painful right now. So we're not there. But if you want to go this route, then you're going to have to think about not just using the beautiful IDE, but also managing the changes. Even if you want to discard everything like that, still, prompt flow is maybe the best tool available right now for testing prompt variations and so on. So I would recommend looking into it, but it's not a simple proposition to go into production with it. Cool. LLM apps. Now we have built the prompts. We have maybe built the flows. Now we have this question of evaluation. Did we evaluate already? Well, we tried. We tried with some data, we tried with some results. But then there are other aspects of what can we actually evaluate. And if we try with large amounts of data, we can't do that just using our eyes and hands in prompt flow. No, we're going to need the evaluation feature. And what we're going to need it for, because we want a systematic way to test LLM solutions, so for example flows, against a set of some kind of measurements. And the industry is working hard to find out these measurements. There are things like coherence, so how coherent is the answer? Is it readable to a user? How relevant it is? Is it just responding to the user's question? How well is it grounded in the facts that the model was given? How linguistically correct it is? Is it good language? Is it easy to read? And then there are different safety factors and so on. There are like, I think, 11 or 12 metrics available for this right now. What Azure AI Studio does for you, it allows you to pick up a flow or other LLM solution. It allows you to give it some test data, and then it unifies them into a pipeline where it spins up a container. The gray box is a container. It evaluates the model with the given data enough times to understand what kind of results it gets out, and then it uses an analysis engine to understand what kind of level of groundedness, for example, or safety, or violence control did actually happen during the process. So you can also test for these content safety features. And then out you get evaluation results. I'm going to be perfectly honest here and say that this is a bit flaky part. It works when it works. I am having trouble getting it to work with real-life scenarios. For example, last night I tried to create a new version of these slides, and I failed because I just did not get the results to work right now. It is a preview, take that seriously, but it is good when it works. So just roughly speaking, what happens is you can select the flow, and you can say this is a question and answer without context. You upload some data. For example, in this scenario, I sent 2 questions. What is the capital of Finland, and which team does Lauri Markkanen play for? And I also provided the right answers. And essentially what would happen then is that there is going to be a delay of like maybe 3 to 7 minutes on a typical data set, is my experience. And then you would get a result back. I did not get a result back, so these images are just from the much of learn. But what you get is a graphic representation of, is everything right? So did we filter out sexual content? Did we filter out self-harm? How good were we in terms of relevance and groundedness in each of these questions? And this kind of provides you the 360 degrees understanding of how did your model perform under real-world data, under repeated executions. Something that you can't really do with prompt flow just using the execute button because it takes too much of your time. Very good, very good. A couple of more points before I finish up, because there are two boxes I did not really cover. Customizing content filtering, has anybody ever done that? The only customer I ever hear about content filters is that can we turn them off? And that is particularly true because some of Azure's content safety features work in a bit strange way when used with finished content. So that's something that happens every now and then. But typically people are quite satisfied with how they work. What you can do here is that you can customize a content filter. But what customization means is that you can pick up different kinds of categories of offensive content like violence, hate, sexual content, self-harm. And then you can set the tolerance from 3 options, low, medium, and high. Well, that's not great. Then you can also have a block list. You can set a block list of different kinds of words you don't want to appear either in the inputs or the outputs of the model.
Is there a whitelist?
No, there is no whitelist. Yeah, this is the problem. There is no whitelist. And Microsoft is pretty sticky when it comes to trying to change the content safety filter into a looser direction. There are scenarios where you want to be able to freely discuss self-harm, for example, let's say a medical help. You want doctors to be able to talk about overdoses of medication, for example. You can't use this user interface to do that. You have to talk to Microsoft and give them your idea and your business case scenario, and then they're going to look into it and maybe enable free use of content safety. I think that's a fairly easy process these days if you actually have a good scenario, but it's still manual work. You can essentially do this to tighten up your content filter. You can have several different content filters, and I think Microsoft's vision here is that you can use this to have sort of a centralized control. So if you're seeing abuse attempts or you're seeing PR risks happen with a B2C chatbot, then you can just go here, not touch the code, but just change the content filter to be more strict. That makes sense. I have not seen real-world use for it. That's why I'm not going to spend any more time on that one. And fine-tuning models. Anyone done that? Yes, I don't think you have to. It's very unlikely that you're going to need it, but you may have to because there are going to be certain scenarios. Don't use it to feed your own data to the model. It's not going to work very well. If you need to have a small model doing a large model's work in a specific scenario, that might work. If you want to change the tone of voice of a model entirely, and you have the time to generate enough sample data for the fine-tuning, it may work. If you do need it, Azure AI Studio has the UX for doing that. So Azure AI Studio is a good tool for this, but I don't think this is the right solution for most of our AI projects right now. So that's kind of where we are. As for recap, we roughly covered all these 7 balloons. What's happening here is that AI Studio is Microsoft's sort of a centralized attempt to make all this happen in a single user interface. It makes sense. There is a lot going on. There is still ways to go before everything is over here. And one good example is that this thing called Copilot Studio, which used to be Power Virtual Agents, is a totally separate thing. It may even remain so, I don't know. But there are several nexuses for building AI solutions. Azure AI Studio is Azure's #1 spot. It's kind of starting to create an abstraction for these cloud AI building blocks, so a higher level of abstraction of building LLMs instead of just calling Azure OpenAI Service from your code. Whether this approach, prompt flow and the friends, is going to be the right one, I don't know. It may be, but the jury is out there. But we're still seeing so much innovation and evolution going on all the time. It's very hard to understand which are going to be the winner solutions for the future. And one thing to understand is if you are a classic .NET developer, you are not going to feel at home here all the time because these solutions are built by and for people with an ML background, with some Python competence typically. So you can get used to that kind of thinking here. It's not that you can't do things with .NET. Apart from prompt flow, you can do everything with .NET. But samples are predominantly in Python. Guidance is written for machine learning and data scientist people. So that's a new set of mind for over here. I don't know if that's going to change over time. Maybe it does. And this is now, as of build, it is GA. Many of the features I covered are under preview, and take that preview seriously because I personally think that it's going to take 1 or 2 years before this is mature. I'm Jouni Heikkinen from Davidson, and that's all I have for today. Thank you very much.
Thank you, Jouni. We have a 40-minute break. Please get some refreshments. All right, all right, all right. Before the drone raffle, we have one last, possibly the deepest presentation. I'm not sure yet, but we have a person here who hasn't missed one Iglooconf, I think.
No.
He's been with us every time we've had this. Have we had this 5 times? I don't know. Sometimes.
It feels like more than that.
It feels like more than 5, that's true. Every time this person gives a presentation, after presentation, I think I couldn't do what he just showed. So let's give a huge show of hands to Alan Smith.
Thank you. Thanks for that, Saki. And it's great that I can come back to Finland again and present. It's a bit different in the summer. We can wear shorts. There's no ice and snow everywhere. It's a nice city in the summer. It's good to see that. So what I'm going to be talking about is inside GPT. I've always liked to understand how stuff works. So when I started playing around with GPT, typing in text, and it started generating cool answers, I'm like, well, how the hell does it do that? What goes on behind the scenes? And I'm been looking into it and hopefully getting a bit of an understanding which I can share with you. Also, give you, hopefully this knowledge will help you to build better chat solutions using GPT. When my friends were studying computer science, they were building compilers. And the reason that they built compilers is to understand how a compiler works, so they can build better code. And if we can understand how these models work, we can understand why they make certain predictions, why they sometimes get things wrong, hopefully build better solutions. So a bit about myself. I am now an AI MVP. I've been in the MVP program since 2005, hopping around various disciplines. I was Azure before I was AI. I do a lot of work with the community. I've got a YouTube channel. I assist with Coder Dojos, also sometimes run conferences. The session I was going to deliver, unfortunately the demos don't work too well in front of a live audience, but I have got the StarCraft stuff on YouTube. So if you were wanting to see about the StarCraft stuff, you can go in and see how I'm doing that on YouTube. Also, feel free to add me on LinkedIn. I'm happy to answer any questions that you've got in LinkedIn chat if you have any questions about this. Before I start, I really want to thank other YouTube contributors who've really helped kind of build my foundation knowledge of AI and machine learning and all things related to this. 3 Blue 1 Brown is missing from this. He's recently done some great videos on the internals of GPT, which I highly recommend checking out. So GPT, we go in and we ask it questions and it magically comes out with these answers. So if we want to make cheese, we can ask it how to make cheese and it will come out with great instructions about how this works. So what I'm going to be actually demoing is GPT-2, which I've got running on this laptop. And this kind of gives you an idea of how well the language models have progressed. So I'm going to start this thing without debugging. And hopefully we can have a conversation with GPT-2.
I'm ChatGPT-2, a friendly chatbot. How can I help you?
What's the capital of Finland?
Capital of Finland is a friendly chatbot.
Clear.
I'm ChatGPT-2, a friendly chatbot. How can I help you?
What is the capital of Finland? It's not working too well. I'll give it another chance.
I'm ChatGPT-2, a friendly chatbot. How can I help you?
What is the capital of Finland?
Finnish capital, Helsinki. Finnish state capital, Helsinki. What is the name of Finland? The name of Finland is Finnish for a Finnish.
Is it nice in Finland?
Yes, it is nice in Finland.
Why is it so nice?
It is nice in Finland because it is a nice place to live.
Are there polar bears there?
Yes, there are polar bears in Finland.
What do they do?
They hunt polar bears.
How?
They hunt the polar bears.
So around about that time when GPT-2 came out, lots and lots of data scientists got excited because you could actually generate text, and it was kind of revolutionary. But it was only data scientists who got excited. You couldn't really deploy this and have something that people would actually be able to communicate with. But the data scientists realized if we make this thing bigger and we train it with a lot more data, we're actually going to get something that we can communicate with. Now, the only thing that these models do is sequence prediction. So the only thing that the model will do is predict the probabilities of the next tokens or next words coming in the sequence. So if we send the cat sat on there, it will predict the probabilities of about 52,000 tokens. And that's basically what all that the models will do. Now, this is a challenging problem because sequences can be of variable length. And we've also got long-term dependencies in these various sequences. So if we're sending in the cat sat on the floor, it had just been cleaned. It had been cleaned, so it refers to the floor. The cat sat on the floor, it had just been fed, so it is going to refer to the cat in that case. And we'll talk later about the attention mechanism, but the attention mechanism does some really complex maths to kind of figure out the relations between all of the words so it can make these good predictions. If we have something that's a lot more complex, a really complex sequence, it says the boy stood in the burning deck in the first line of this poem. On the second column, it's saying upon his brow he felt their breath. And the models will understand that his refers to the boy, which is mentioned right at the beginning of the sequence. And this is really what the GPT models are doing. The sequence order is also important. So if we have this set of words, the film was not bad, in fact it was very good, versus the film was not good, in fact it was very bad. Exactly the same words, but we're just changing the order and we're completely reversing the sentiment of that particular sentence. So looking at the actual what the model is doing, I've got a demo that basically shows how the sequence prediction works, and I think it's this GPT fundamentals. So I'm going to set this as the startup file and just run this without debugging. And we'll basically see what GPT-2 is doing to make these actual predictions. So GPT-2 is open source. I've downloaded it from Hugging Face. So if we send the cat sat in the, we get all of the actual percentage predictions for what the next token is going to be in that particular sentence there. So it's saying that floor with 7.64%, and then we've got bed, couch, ground, and so on. And there are about 50,200 tokens in the actual token vocabulary. And we'll look in more detail at what tokens are a bit later on. You can see Helsinki is the capital of, and we've got Finland there with 42.77%. And then Estonia and Russia are down here, so I'm not sure where it's got training data from that. But basically, there is a probability that each of those tokens could be the next one in the sequence. And in the majority of those tokens, the probability is very, very low. It understands languages, even GPT-2. If we're using system dot, then it's specifying, things like runtime, console, security, text, exception, whatever. Any Python programs in the audience? So if you're programming Python, you import NumPy as NP, usually when you're writing Python code. So that's got quite a high probability there. And the king of rock and roll is Elvis. Tokens are not always full words. You can see that pres is the next predictable token. So it should be Elvis Presley. However, 2.76 chance that they may mean Elvis Costello, because it's got cost there as that token. And sometimes there can be a really high probability. If the King of Rock and Rolls is Elvis Pres, there's a really high probability that the next token is going to be Lee. My favorite animal is the. You can see that we've got dog here. And if we zoom in way around here somewhere, I think. It's not zooming in on me. Oh yeah, you can see polar there at 0.23%. And then if my favorite animal is the polar, you can see that bear is going to be really, really high probability there. So that's all really that the models are doing. They're actually just working with the probability of these various sequences. Now, a lot of people say that these models are great at understanding text. This is the actual diagram from the white paper, Attention is All You Need, that shows the architecture of the transformer models. And the idea is that we send in text and these things are great at understanding language and understanding text. It's not entirely true. The neural networks don't do text, they don't understand text. So we have the concept of tokenization. We convert our text into tokens. This is something that most people who work with large language models will get. They understand the concept of tokens, that you've got, so many input tokens that you can send in. The model accepts so many tokens, and we pay money for processing these particular tokens. Now, tokens are not words. You can see that the text tokenization, the word token is basically one token, but then ization is something that you can stick on the end of most words, especially if in American you can put ization on pretty much the end of anything and make it a new word, like hospitalization, burglarization, computerization, and various things like that. So what it does is it basically figures out the most efficient way of breaking down the sequences of characters in the training data, so that it can be usable and processable and understandable by these large language models. So, 3 really important things. Firstly, these tokens are common sequences of characters found in text. They are not words, they're common sequences of characters. And when we say text, we really refer to the text in the training data, which is mostly English. So it's really common sequences of characters that are found in the English language. The models understand the statistical relationships between these tokens. This is really important. I would argue that large language models don't understand language. They understand the statistical relationship between tokens, because the models never see the language. All they see is this sequence of numbers. And as far as the model is concerned, these could be musical notes. We could tokenize music, and we could send in, the tokens for different musical notes, and it will predict the next note in a piece of music. As far as the model is concerned, it's just using stats to predict the most probable token. However, this is really important as well, maybe except for GPT-2, but the GPT-3.5 and GPT-4 and later models and the other models that we've got there, they excel at producing the next token in a sequence of tokens. I would argue that that's not entirely true. They don't just predict the next token, they predict the probability distribution of all of the tokens. So these 50,200 tokens, we get the probability distribution of them. And that's important because we're going to use temperature to affect how it actually selects those particular tokens. The last presenter mentioned the word stochastic, which basically means random. Data scientists like to use long words to confuse people, so they won't say random, they'll say stochastic, so you have to be a data scientist to understand what they're talking about. But there's a randomization in there, and it will generate random responses depending on what we set the temperature to. So you can see there we've got a sequence of text which we've tokenized into tokens, and if we're in English, it will look like this. It's an array of integers, and that comes out to 45 tokens. You can see that the word the is represented differently. So the first the does not have a space between it, it has a capital T, and then we've got a the with a space between it, that comes out as 363, and then the lowercase, starting with the lowercase t, that's 262. But most of these words, or pretty much all of those words, are individual tokens, prefixed by a space, because it doesn't make sense to have space as a token, because then you probably need about 90 tokens to represent that if space was its own token. Also, the numbers for those, does anybody see any significance about the number representations of comma and dot? It's the ASCII character set, the character codes for those various characters. So the first 256 tokens are just basically character codes for characters. Then that allows it to basically use any type of text. If we go into Swedish, you can see that it's not as efficient at representing the language as tokens. We've now got 83 tokens instead of 45. If we go to Finnish, 103 tokens there. We'll get back to that later on because that affects the efficiency and the understanding of the language. The worst one I found was Telugu, which comes out at 622 tokens. There's only 247 characters. So it's using kind of the character codes where the character is represented kind of by more than one actual token. So this is the actual tokenization efficiency of the language. You can see English is 1.0, Telugu is 8.8, and Finnish is round about here somewhere at 2.2 between Polish and Chinese. And that almost, it kind of correlates, but not really exactly. It's not a straight line if you kind of plot these on a graph. It kind of correlates to the language understanding for GPT-4. We've got 85% for English and we've got 62% for Telugu. This doesn't show Finnish on there, but Finnish is going to be, somewhere down here somewhere. It's less efficient at understanding Finnish than it is as English. So one thing that a lot of people say is that English is the new programming language, because if you're in the last session, there was mention of prompt engineering. Instead of writing code to tell a computer how to do something, we're writing English in the prompt to actually tell a large language model what type of response we want. And the code is pretty much boilerplate code. It takes what we want, throws it at the API, gets the response and sends it somewhere else. It's not really doing that much logic. All of the kind of logic that's driving these LLM applications is in the way that we write the prompt. Several reasons why I say that. The GPT models are more accurate with English because the tokenization is more efficient, and also the understanding is better with English because there's a lot more training data in English than other languages. Billing is based on the number of tokens. So if you're sending English to the models, it's going to be cost less than sending Finnish or Swedish or certainly Telugu. Throughput is based on the number of tokens per second, and your quota is based on the number of tokens per minute. And also, models have a maximum number of input tokens. We're developers. If we can make something that's going to be, 20% faster, it's going to cost 20% less, it's going to, be able to process 20% more information, we'll do that. It's an easy win to use English. Now, even in projects where we're working when the language is in Swedish, the input data is in Swedish for our retrieval augmented generation stuff, the output is going to be in Swedish, we use English for the prompts. And we just ask it to provide the output in Swedish. It's fairly easy to do that. And just to give a demo of that, I don't demo this because it gives unpredictable results and it runs very slowly. I asked it how to make cheese in Telugu. This was a GPT chat, and the English, if you remember, the English was quite a good definition. And this is what it came out with in Telugu, suggesting using something called cheese powder, which I've never heard of. Then it gave up. And it switched back to English, and then it offered to create a poem or a story, or if we wanted any kind of other response. Also, here is the image of the Frozen movie characters Elsa, Anna, Kristoff, Olaf, and Sven in an ancient autumn-bound forest of an enchanted land that you requested. I hope you like it. So it kind of thought that when I asked it how to make cheese, that I wanted it to draw the Frozen characters in a mythic woodland setting. Now, that is an extreme example, but it does give you an indication that, there is that graph. As we go down and use languages other than English, it's going to have a better understanding of those languages. So iterating the tokens, we can see the tokens that are used in the model. So if I drop back here and just run iterate tokens, what this is going to do is just basically go through and show you the tokens. Listen, did you hear the bell sound? Because one of the ASCII characters is the bell. So when it prints out that token, it basically makes the bell noise. But as you can see, the first 256 are just basically ASCII characters, and then it gets into bits of words. And as we scroll down, it's basically bits of English words that we've got there. So it makes languages like Finnish by just piecing together these small word combinations. Yeah.
Do you know the size of the vocabulary
It's about 50,200 and something, I think.
Is it something they disclosed?
Yeah.
Okay, cool. Thank you.
Yeah, so there is a website that you can go to, the tokenizer. So this is for GPT-3.5 and GPT-4. So what we can do is we can just whack some text in there. And that's what I was doing. And it just shows the actual tokens, and we can see the token IDs. And I think it is the same number of tokens that they're using pretty much as they're using in GPT. I'm not sure. Oh, this is coming soon, the GPT 4.0. I'm not sure if they've increased or modified the tokenization of vocabulary there. Okay, so really what we're doing is sequence prediction. Given a series of tokens, the cat sat on there, it's going to come up with a probability distribution of the next token. So it's saying the cat sat on the floor is going to be the most probable token. Now what we can do is just take the most probable token, stick it onto the end of the input, send it through the model again, and we get a comma being the next probable token. We can get the next probable token, stick it on the end, send it through the model again, and is going to be the next token there. So that's what's happening when we are chatting with GPT-4, when we're working in the Bing portal. That's why we see the words coming out one by one. It's continuously running this through the model many, many times to be able to get the next probable tokens. So we can look at the next token prediction. I think that was the demo here, 3A. Let's set this one as a startup file and do a Control F5. Oh, I'm going to change something before I do that, because I understand we've got to make lots of references to polar bears. Is there a prize for the most polar bear references? So what I'm feeding in is my favorite animal is the polar, and it should come out with bear as being the most probable prediction. Enter some text. If I press enter, it's just going to take that, save me typing it in and misspelling it. And you can see like 98.44, we've got bear. Now, if I press enter, it's just going to slap the next token on the end, send it through the model again, and you can see that the next probable token is the full stop. And then we've got it's a great companion for me, full stop. I love the fact that I can see the polar bear from the outside. I love the fact that I can see the polar bear from the inside. Yeah. So if the only thing we do is just whack the most probable token in, it's just going to generate, really, really boring, repetitive text. So if you go to a party and you say the most predictable thing all of the time, nobody's going to talk to you because it's going to just be the same type of thing. It's going to be really boring. So stochasticity or randomness, we want to put some randomness in there. And we'll talk about temperature a bit later on about how we can use temperature to vary the output and other things like top P as well. However, it doesn't stop at tokens because neural networks don't really do integers. They deal with floating point numbers. So what we want to do is to think about word or token vectorization. Has anybody heard of embeddings and vector databases and all of this wonderful stuff? So embeddings and vector databases, this is another way of being able to store information in systems to make them more retrievable by large language models. And the idea is that if I say, what's the weather going to be today? And we're doing a text search, then it's just going to search for those actual words. What is the weather today? And it just basically does a text search or a word search. However, searching by sentiment is like saying, what's the weather today? Will it rain today? Should I take an umbrella today? They all have similar sentiment, but they all use different words. So in some cases, you may want to use vectors for searching, and also for being able to do calculations on words in NLP, or natural language processing. Word vectorization is a thing that people do. Now, cheese, this is the actual embeddings for the token of cheese in GPT-2. It is a big sequence of floating point numbers. I think there's 768 of those. And depending on the system that we work with, we'll have a different number of embedding vectors. We have models that can take text and convert it into embeddings, and then we can compare these embeddings, and we can compare words to see if they are of similar sentiment. We have a project at work where it was loads and loads of news articles, and the customer wanted us to group very similar news articles together. So even though the text was different, we could find that these news articles are talking about the same thing. So we basically did text embedding on the news articles, and then we did some clustering algorithm, and we could actually group together news articles that were basically about the same thing and identify those at those groups. So a lot of the stuff that goes on when we're doing natural language processing in AI is basically doing maths with vectors that represent these words. Now, we can't think in 768 dimensions. Humans can think in 3 dimensions. We understand the concept of 3 dimensions. We also, because many of us have built websites, we understand about the color space. So Azure is 0127255. That's a color code for Azure. But the way that a data scientist would represent it is 0.51. We deal with floating point numbers between 0 and 1. So this allows us to project colors into this 3D space. And what we can see is that similar colors are basically at similar locations within that 3D space. We get that. But also the same thing happens with words, as we'll see later on in a future demo. Now, there's different ways of figuring out if these embedding vectors are similar to each other. You may talk about the Euclidean distance or the cosine similarity, and there's various other methods. It's just basically doing maths to figure out if these words or colors are similar to each other. Now, if we look at the color of Azure, you can see that that's 0.51. If we look at the color dark Azure, you can see that that is sitting along the line as Azure. It sits on that line. And you could argue that this is a similar color to Azure. It's the same kind of shade, but it's just, no, it's the same like color. It's just a darker version of that color. And then cyan, you can see that that's quite different to Azure. And that's in a different space there. However, if we look at the Euclidean distance, which is kind of the distance in 3D space, you can see that cyan is closer to Azure. If we look at the cosine similarity, that's relating to the difference in the angle between those. And you can see that all of the kind of colors that would sit on that line have the same cosine similarity. They're at the same angle. So sometimes we use cosine similarity that compares the angles. So how many people recognize that? I saw a big lot. That's fantastic. I saw a big pile of board games in the Azure office when I was there last night. So Carcassonne. This came from, I was giving this presentation at the DevSum conference in Finland, and before I went on stage, I was talking with another guy at work, and he was talking about vectorization of board games. You know, how can I do embedding and vectorization of board games to find similar board games? And I thought, oh, that's cool. I'll do a slide on that and stick it in my presentation. So I did this just before that. And what he was wanting to do was saying, if you like Carcassonne, what other games are you going to like? So what I'm plotting on here, this is in 2 dimensions. I'm plotting the age and the game time. If we put Star Wars Rebellion on there, you can see that the game time is about twice as long and the age is about twice as old. So that game is not going to be similar to Carcassonne, even though it's sitting on the same angle. Whereas Ticket to Ride is a slightly longer game time, slightly higher age. That's closer to Carcassonne there in that 2D space. So in that case, maybe we'd want to use the Euclidean distance. And there's different mechanisms for doing these actual vector similarities. We can also do something called dimensionality reduction. So if I drop into this website here, which is the embeddings projector, this has a database which is called Word2Vec. And when you start doing file new project with natural language processing, Word2Vec is one of the data sources that you go to. So this is 10,000 words. And what we're going to do is to reduce the actual dimensionality and find what we call nearest neighbors, which is figuring out which words have similar sentiment or similar meaning by reducing the I don't know how many dimensions that they've got. Yeah, they've got 200 dimensions there in each vector. So reducing those 200 dimensions to 3 dimensions. And what this does, my laptop is pretty slow, but what this does is basically puts the words that have similar sentiment together in these similar locations. So if I search for the word October, and I search for 10 words, using cosine similarity, we basically get the months appearing. So these are the nearest neighbors to October. And we can see that they appear round about the same place in this 3D cloud. And then as we go to different locations. I don't know if this is organized itself yet, but electrons, atoms, benzene, and various things, molecules are in the same kind of area in that 3D cloud. And what it will do is basically group together words that kind of mean the same thing into the same actual location there. So that's kind of what's going on in the language model, but it's using tokens rather than words for that actual vectorization. We'll see how that works a bit later on when we go into the actual maths. Now, one of the things that these large language models do is they handle the concept of a transformer, which is a way of being able to figure out what we call the attention, which is kind of how these words are related to each other. So this is what the actual architecture looks like, and it came from a white paper called Attention is All You Need. It's quite a tough read if you want to actually go through it. Another thing that's a bit confusing about the Attention is All You Need white paper is that it was written about translation. It was talking about translating two languages. Well, we can use transformers for translation, but most of the time we're using them for GPT, we're using them for sequence prediction. So you can kind of get rid of this output embedding, which is the positional embedding for the output language, and just focus on this bit, which is the actual input embedding. And this is what happens when the actual it's kind of basically a list or an array of integer values comes in, which is the actual tokens that go into the model. We're going to do the input embedding, and then we're going to do the positional embedding, and then it's going to go into these multi-head attention spans. So we've covered tokenization. We take the cat sat on the, and if we convert it into the tokens, we get these numbers like that. And then what we're going to do is the token embedding, which is figuring out the actual vector, this was it 672 dimensional vector for each of the actual tokens. So we basically do the tokenization like that. Within the model, there is something known as a token embeddings table. And this is just a big two-dimensional matrix of floating point numbers. There's 768 columns in it, and there's 50,256 rows. So for each token, there's the 768 actual embedding vectors. So this is easy. We just basically take 464, 3739, 3332, 319, and 262. Do the lookup in the embeddings table, and that's going to give us our actual embedding vectors. And that's basically going to be 768 by 5, because we've actually got 5 input tokens. So that's going to give us the embedding vectors. The other thing that we need to know, because the position of the words is also important, is we need to figure out the positional vectors. So there is another lookup table where we actually do a lookup for the positional vectors. The positional vectors also has 768 columns. However, the number of rows is equal to the maximum number of tokens that we can send in. So if you can send, say, 4,000 tokens into the model, this thing will be 4,000 by 768, and it will pick out 0, 1, 2, 3, 4, 5 for the actual tokens, and just grab those positional vectors. Now, these are created from sines and cosines of various frequencies, and these are basically fixed, whereas the embedding vectors are basically trained, and all those values are set when the actual model is training during the training process. So once we've got the embedding vectors and the position vectors, we can add those two together, and that gives us our encoding input values, which are these actual vectors there. So if we whiz back a few slides, what that is doing is basically this bit here. We've got the input encoding, which is taking the inputs, getting all of the vectors. And then the positional encoding is just taking, you can see that bubble has a sine wave in it. It's using those sine wave-based vectors of different frequencies. And then we've got the add sign, we add those together, and then this goes to the multi-headed attention. Now, we'll cover that in a bit, but what I'm going to do is just step through and breakpoint onto the actual model itself. So, just see how I'm doing for time. Seems to be okay. So what I'm going to do is this next token prediction, I'm actually going to run this in debug mode, but I'm going to change, because I use the example of the cat sat on the, rather than the my favorite animal is the polar bear. I'm just going to comment that out and drop that. And then I can run this in the debug mode. So I've downloaded the source code for the GPT-2 from Hugging Face, and it's written in PyTorch. which is one of the frameworks that we can use for machine learning. I think it's not the original one. I think the original GP2 was written in TensorFlow, but this is a PyTorch version of it. And if we go into the watch window, self is basically Python for this in C#. So it's telling us what class we are in. So we're currently in the GPT-2 model, and we're just basically setting up the actual model here. So if I run F5 again, we should get saying enter some text. I press enter, and the text is going to be the cat sat on there. So we're now in the GP2 head model, and we can see the input IDs. So these are the actual integers for the cat sat on there. If we drop back here, I mentioned that the model never actually sees the text, it only sees the token. So this thing is the tokenizer, this thing is the model, and here we just get the input IDs by calling tokenizer.encode and passing in the text. And then we call the model with the input IDs. So we're just sending that list of integers into the model, and we're getting the outputs from the model. And we'll look at what those outputs are a bit later on. So where were we in the code? Okay, if I just press F5 again, we'll get to the next section here. So here you can see we've got the input IDs. We've also got the position IDs. Because there's 5 tokens, the position IDs are just basically 0, 1, 2, 3, 4. That's just a list of integers there. And this is when we do the input embeddings. We've got this WTE. So self.WTE, this is the actual lookup table that contains the, if I just clear the immediate window, contains all the embeddings. So this is just basically an embeddings table that we've got. And what we're doing is we're just basically passing in the input IDs, and that's going to return the actual input embeddings. So if I step over those 2 lines of code and we go back to the watch window, you can see that the input embeddings is this big tensor, and this is basically containing lots and lots of floating point numbers. The actual dimensions of this is 1 by 5 by 768. Now, when you're working with large language models, they can usually, when you're working with most neural networks, they can usually process a batch of inputs. During the training process, you train in batches. When you're training an image model, you send it, say, 10 images in a batch. So the first number there represents how many items there are in each batch. I'm only sending in 1 piece of text, so that's always going to be 1. The second number represents the number of input tokens, which is 5, and then we've got 768, which represents how many floating point numbers we've got in each vector for the embedding of each token. And then if I step over again, we've got the position embeddings. So the position embeddings, this uses the token encoding, and this is just using the position encoding. We pass in the position IDs, which is 0, 1, 2, 3, 4, and then we get the position embeddings. And then the next thing to do is to add these 2 together. So the input plus the position, that gives the hidden states. So that's a kind of representation of the words with the actual kind of meaning or the sentiment of the word, which is in the embeddings, and the position of the word. So we know what the words mean, and we know which position they are in. That's giving us 2 of the things that we need. But what we also need to know is kind of how the words relate to each other. And that's really what goes on in these multi-headed attention blocks. Now, you can see that there is an NX, and basically in GPT-2, in each multi-headed attention block, there is basically 12 attention heads, and there are 12 layers of attention heads. So there's going to be 144 of these multi-head attentions. So the same kind of attention calculation is taking place 144 times. So what goes on in there is this actual maths. This is the actual formula for doing the calculation on attention. And it works by using a query, a key, and a value. And what it's really doing is taking each token in the sequence, comparing it to every other token based on some type of a criteria of how those actually relate to each other. So to generate the key query and the value, we take the encoder input values. So this is the stuff that contains the meaning of the word, or the sentiment of all of the tokens and the position of all of the tokens. And that's 1 by 5 by 768. We send it into a convolution layer. And this is going to be different for every one of those attention heads. And there's 144 of those. So dependent on the actual numbers that are set in the training for the convolution layer, we're going to get different representations of the input that are going to be used in the attention mechanism. So this is coming out as 1 by 5 by 2304. It then goes into a split operation to get out the keys, the queries, and the values. So this is going back to 1 by 5 by 768. The top one is the key, the middle one is the query, and the bottom one is the actual value. Now, because there's 12 heads, we then actually split that vector into the keys, queries, and the values for each of the 12 heads. So that's 1 because there's 1 batch, 12 because there's 12 heads, 5 there's 5 tokens, and 64 of those because that's what happened when you divide 768 by 12. That gives you the key, the query, and the actual value. And those are actually used for calculating the attention, which is how the words relate to other words. So, Saki, can you stand up, please?
Yes.
Yeah, so if you imagine that we're processing everybody in this room, and we're all tokens that are going on, and what we've got to figure out is the relationships that we have to one another. So this will happen for each person in the room, but right now it's happening for Saki. He's going to be the query. So he's a current token that the model is focusing on. And then the key is going to be a token from the input sequence that the model is comparing to the query. So each person in the room is going to have a comparison to Saki, and it's saying, okay, like, how do you relate to Saki in some way? And the value is really how we're actually doing that comparison. So how many people work at the same company as Saki? So there'll be quite a strong relationship between the people who work at the same company as Saki. How many people have been drinking with Saki on an evening? Lots of people there. How many people have survived? The others are somewhere else. So for every kind of, in every attention head, it's kind of doing a slightly different comparison of how it relates to that. And you know, you may have gone to school with Saki, you may be his neighbor, you may be in the same darts club as him if he plays darts. And all of those different relationships, all those different attention heads will look at a different way of being able to actually compare those words. And it will basically build up a kind of a strength of how much connection you have to Saki based on all of those different bits of information. Thanks for that. You can sit down again. So that's really what's going on in the attention span. Now, it's kind of easier to explain the concept of what it does rather than the maths of what goes on behind it, because it's all vector maths. Basically, everything that goes on with working with neural networks is processing these really big vectors. This is really good because everything that goes on in the graphics for 3D games is about processing the same types of vectors, which means that gaming cards are really, really good at being able to do large language models. And because there's millions and millions of gamers in the world, a lot more gamers than there are data scientists, it means that GPUs aren't as expensive as they would be if gamers didn't use them for 3D maths. I also heard that, was this yesterday or the day before, that NVIDIA is worth more than Germany currently. The NVIDIA stock price is more than the German stock market. So NVIDIA is doing well out of this, and a lot of this is driven by, you know, having to do all of this maths to be able to train these models. But basically what we're doing is we are multiplying the query by the key. We're then dividing that by the root of 64 because that just seems to work better. And 64 is basically the actual number that we've got here. And that gives us, once we've put it through the actual softmax algorithm. And softmax is just a way of ensuring that all of these floating point numbers in all of the rows and the columns will add up to 1.0. And what that's giving us is the words and how the words relate to each other using different criteria. We then multiply it by the value and we get this, which is the attention. Now that basically has the meaning, the position, and what's really important, the relationship to other words in the sequence. So we can see a bit about how that maths works. I think my breakpoint is still set in the code. So if I go to the next breakpoint, you can see here, this line of code is basically getting the query, the key, and the value. And it's doing a couple of operations at once. I think I said on the slides that it does, if we drop back to the slides and I whiz up a bit. It goes through that conv 1D, and then it does a split, and then it does the actual split heads. And it's doing all of these operations at once to give out these keys and queries and the values. So if we drop back to the code, this is basically using the convolution there, passing in the hidden states, and then it's doing the actual split. And then we do the query, the key, and the value, doing the actual split heads here. So that basically splits it up into the 12 heads. So if I step over that row, we should see that we've got the size of the query, the key, and the value, 1 by 5 by 768. And then when we do the head splitting, it's splitting my head, all of this maths. We've got the 1 by 12 by 64. So that's basically going to be those attention heads. Now, if I keep pressing F5, you can see that this is happening a lot, because there are 12 layers and there's 12 attention heads in each layer. So it's going to have to be 144 times until we actually get the output. And then that's going to be what the actual output is with the actual predictions of those word probabilities. So go back to the slides. So we've done that calculation and we're getting out the actual values from that. And what's kind of happening in the maths, if we could go in and see and visualize and understand this, we've got those two sentences I had as examples earlier. The cat sat on the floor, it had just been cleaned. The cat sat on the floor, it had just been fed. So if you mention the word it a bit later on, what does it refer to, or what does he refer to, or she refer to when I'm talking about something? Maybe it was something that was mentioned earlier on. So these actual tokens will have their vectors, their sentiment vectors. And if we assume that this is in 2D space rather than 768-dimensional space, they will basically look somewhere like that, sitting in this actual space. And they'll have a certain distance from each other, and the closer that the words are together, the more connected they are. We saw that when I was looking at that visualization cloud. All of the months are in the same shape. All of the kind of scientific words are in the same place. So the word it hasn't actually got any kind of attention to any other words. It hasn't kind of been linked to any other words. But these attention calculations, because we're taking the first example of the cat sat on the floor, it had just been cleaned. When we've been through all of these layers, it will modify the vector values of it to put it to closer to floor and closer to clean. So it now is more similar to floor than it is for cat. Now, it could be mentioned several times, but it's the particular instance of that token within that actual sequence that is going to have its sentiment shifted, dependent on where the other words and how it's connected to each other words. So that's really what's going on within the attention mechanism. And as I mentioned, there is 12 layers and there's 12 attention heads in each layer. It's also doing a bit of the normalization and feed forward and softmax and so on towards the end to actually figure out what's going on in the actual network. Now, we can actually visualize this. There is a great website, I think it was part of the Hugging Space stuff, but it's this one here. And what this is doing is actually displaying a visualization on the BERT model, which is fairly similar in terms of complexity to the GPT model. So what we see here is the various sentences, and you can see all of the connections between the words, and you can see the actual view of the model. So these are all of these attention heads. You can see that it's 12 along by 12 down, and it's kind of showing graphically the actual connections and links of all of these words. I've not really experimented with it that much to see all of these actual values, but what it's doing is kind of providing the internal visualization of what's going on with the attention in all the different layers of that network. So that's a site that you can go on if you do want to experiment with and explore how that stuff works. So how can we parameterize this and get better results? Because we don't want it just repeating and just giving the most probable token. So we've got something called temperature. And the sampling temperature can be between 0 and 2. And higher values like 0.8 will make the output more random. Sometimes if you go up to 2.0, the output just gets completely corrupted. So I wouldn't recommend going much above 1. The portal usually prevents you from going above 1. But using temperature, that can also affect the output of the model. So I've got a temperature demo here. If I go to temperature theory, set this one as a startup file and just do Control F5. Remember, this is GPT-2. It's not that great at doing predictions, but what this should do is basically show, with using a temperature of 0, you can see that the text is coming out there and it's very repetitive. As we increase the temperature, the randomness or the stochasticity, I love that word, of the the actual outputs is changing. And here, by modifying it and pumping up the temperature, you can see that we're getting more creative outputs. You can also get inappropriate outputs. I've been doing this presentation, suddenly the whole audience falls about laughing, and I have no idea why, and something inappropriate has come up on the screen. So I'm a bit concerned about this. But you can see that as we push up the temperature, we do get more creative outputs there. But we've also got other parameters that we can modify. So if I drop back to the slides, we've also got, basically there's maths using softmax. If you played around with neural networks, you will know what softmax is. As I mentioned, it's a way of being able to get a series of floating point numbers into a percentage distribution. And by dividing by the temperature, that modifies or shifts the magnitude of that array. And that will affect the probability distribution because it's using logarithms and stuff like that. It's a nonlinear function. And this, I saw that and thinks, well, what if temperature is 0? Bad things are going to happen because it's a divide by 0 exception. So in that particular instance of the model, you can't use a temperature of 0. You just use a very, very small number, and that will affect the probability distribution balance. So I've shown that demo. We've also got top P, which is another mechanism for being able to actually control the way that we get the probability distribution. So top P, if I specify a top P as 0.1, it will only select from the top 10% of the actual answers. So if the top P is 0.1, it can be floor or it can be bed, and it's most likely to be floor, but it can never be couch. With a temperature of 0.1, it could be couch. I've got an animation that shows how that works. And top P is basically used as an alternative to temperature, or it can be combined with temperature to limit the actual results and stop it from generating unpredictable tokens. You can see here that the top P is set by default to 0.95, which means that the 5% of really obscure tokens that it shouldn't be giving outputs to are not going to be returned in the output. So just to finish off with, I created just during lunch break, I think, this actual animation, which basically shows what happens as we modify the temperature and modify the top P. So you can see when the temperature is 0.75, and as we increase the temperature, the probability of floor is increasing here, and also the probability of floor is increasing slightly with the top P. But when we start to get around here, you can see that the actual probability of these tokens are actually disappearing from the probability graph. The way to think of this is when you go to the fun fair, there's one of those wheels that you can spin, and there's a tiny little wedge which is the top prize, and that's the probability that it's going to land onto the top prize unless they've put a weight on the wheel. But kind of like spinning one of those things, that's going to show what's going to come up. And as we reduce the temperature in the top P, it affects these probability distributions in different ways. And you can see as we go down and as this approaches 0, then the actual probability of it being floor is going to get to 100% in both cases. But it has kind of different ways of modifying the probability distribution there. So hopefully that's been a good introduction to the GPT and the large language models. I will be around if anybody's got any questions. Thanks very much for listening. And I understand that Saki wants me to show some kind of thing that we've got to do something with.
Let's not do it yet. First, Alan Smith.
Thank you.
And then you can do this. And after you guys have, you can start doing it, of course. But to stream, we thank you for attending and following Iglooconf, and we wish you all the best. Have a nice weekend. Adieu.
Thank you.